So we'll wait for 2 or 3 minutes. Some more people are joining with us. Okay. So good morning to all and all. Good morning. So please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Okay, fine. So let's continue with the next topic, that is transmission voltage levels, right? Transmission voltage levels in India. Transmission voltage levels in India. See, particularly these transmission voltage levels, we are going to take up in different ways. First, we are going to say that as high voltage transmission, or you can say simply HV transmission. So first one we are saying here, HV transmission. You can call it as high voltage transmission. HV transmission. Generally, voltage levels of 11 kV and 33 kV will fall in this category. Okay, 11 kV, 33 kV will fall in this category of HV transmission. Next one, extra high voltage transmission, so-called EHV transmission, we can say. Extra high voltage transmission. High voltage transmission. So you can call this as EHV transmission. So generally it will be 66 kV, or you can say 132 kilovolts, and then 220 kV. 220 kV. So these are coming in the category of extra high voltage transmission. So in some places, maybe in the definitions, the people used to call medium transmission voltage levels and all, right? Medium high voltage levels and all, 66 kV, 130 kV in that manner. But in general, you have to think in this manner. Extra high voltage transmission, 66 kV, 132, and then 220 kV. And we have one more level like modern EHV, modern extra high voltage, right? Modern extra high voltage, transmission. So you can call this as a MEHV level. So it will be 400 kV. MEHV level, it will be of 400 kilovolts. Modern extra high voltage level. And last one we are going to call it as ultra high voltage level, else you can say UHV level. Ultra high voltage level, or in bracket you can write this as the UHV level. See, generally ultra high voltage level in the sense voltage above 500 kV. I'll write in bracket here. Above 500 kV is going to be called as ultra high voltage level. Okay. Above 500 kV, what is the voltage level we have in India? Above 500 kV, what is the voltage level we have in India? 765 kV. So I am saying here simply 765 kilovolts. But basic definition of UHV is what? Above 500 kV itself is going to be called as UHV. But in India, we have a level of 765 kV. Okay. Now, what is the highest voltage transmission in India? What is the highest AC voltage transmission in India? That is 765 kV. So this is the highest AC transmission voltage. AC transmission voltage level in India. Voltage level in India. Highest AC transmission voltage level in India, that is 765 kilovolts. Okay. We have this line in many states. I think in Madhya Pradesh, we have one line. In Sipar to Sioni. We have this line, 765 kV line. Okay, so let's move ahead. Let me think about the distribution levels, distribution voltage levels now. So I'll say in the next slide, distribution voltage levels. Yeah. Particularly, we have two types of distribution levels here. One, you can say primary distribution. Next one is a secondary distribution. A 66 kV is also there right now in India. 66 kV is also there. You should not say it's not using. We have that, as well as we have that 110 kV also. In India, we have one more level of 110 kV. 110 kV is also there in India at some places. Yeah. Distribution levels, we have two. One is a primary distribution. Next, it was a secondary distribution. Primary. first one we are saying as primary distribution. Else we can call it as a high voltage distribution also. HV distribution also we can call it as HV distribution. High voltage distribution, HV or HT, high tension, like that also the people will call high voltage, high tension, right? See, generally it will be 11 kV voltage. High voltage distribution, it will be of 11 kV. 11 kV, moreover, it's a three-phase system, what we are discussing now. Three-phase, three wires. Three-phase, three wires. So what are the three wires? You can say simply phase conductors. Maybe phase A, phase B, phase C. We can call simply like this. So phase A, phase B, phase C. Okay, only three wires. We don't have any neutral wire in this one. We don't have any neutral wire in this one, particularly for 11 kV, 33 kV and above levels. Above levels up to 75 or any level, whatever you say, you don't have any neutral wire. We have only phase wires existing on the towers. We don't run a separate neutral wire here. It's not necessary. It is high costly also. Okay. Yeah. So next one we are going to call as secondary distribution. Secondary distribution. Or you can call this one as LV or LT distribution. LV or LT distribution. So this is a voltage what we use to get for domestic supply. Right? So this is a voltage which we are going to get for domestic supply, particularly for three-phase level. It is 415 volts. Three-phase. It's a four-wire system. It's a four-wire system. Four-wire system means what now? We have phases A, B, C, and then we have additionally neutral wire also. Okay. So let me show. This is a phase A wire, phase B, phase C, and additionally we have one neutral wire also running. Additionally, we have one neutral wire also running like this. It's a three-phase, four-wire system. Secondary distribution. And we have one more voltage level in case of secondary, that is single-phase voltage level. Single-phase voltage level, that is 220 volts. Single-phase, two-wire system. Single-phase, two-wire means we have two wires like this. One wire is going to be called as a phase conductor. Phase, it may be either A or B or C, any one of the phase wire. Either it may be phase A wire or phase B wire or phase C wire. And last one we are going to call as a neutral wire. Neutral wire. Okay, so I think all of you getting this one. Yeah. HV, HT both are same. That's what I said earlier also. See, actually, whatever the voltages have given here, particularly for single phase and three phase, 415 volts and 220 volts, these are standard voltages. Standard voltages. Maybe operating voltages are a bit different from this. In some cases, rather than 415, you might have seen 400 volts. Sometimes you might have seen 440 volts. In place of 220, you might have seen 230 volts, some places. But these are standards, what I am saying. But operating voltages might be a bit deviated from these numbers. Operated voltages might be deviated from these numbers. Okay, so these are standard voltages, what I am saying. So one of the conclusion we can make from this now. Listen, one of the conclusion here is we are going to run the neutral wire only from the secondary distribution onwards. We don't have the neutral wire in the primary distribution, as well as we don't have the neutral wire in the above levels also. Okay. Why we have to run? Why we have to run that neutral wire in the secondary distribution? What is the reason to run the neutral wire in the secondary distribution? That is to satisfy the single phase domestic consumers. Because most of the loads what we have in our system are of single phase type only. Domestic loads I am talking. Okay. So for the domestic load or house, we can't supply two phase wires, right? We can't give a supply by two phase wires. We have to give one phase wire as a forward, and we have to provide the return path by means of a neutral wire. Okay. For that purpose, we have to provide one neutral wire provision in the secondary distribution. Okay. So I'll write that statement if you want. Simple. neutral wire exist in secondary distribution system to meet the requirements of requirement of single phase domestic consumers. To meet the requirements of single phase domestic consumers. Okay. Next thing, what is the tolerance allowed for voltage variation? Yeah, please kindly complete it. Yeah, tell me now, what is the tolerance allowed for the voltage variation? Tolerance in voltage variation. Yeah. So how much percentage of voltage variation we can accept? Generally, we have two ways of saying this. Some people will say plus or minus 5%. Some people will say plus or minus 6%. According to Indian standards, it will be plus or minus 6%. According to Indian standards, IS. Okay. Whereas, according to the universal standards or IEC standards, you can say international standards, it will be plus or minus 5%. Plus or minus 5%. Maybe in some local examinations, maybe state examinations and all, right? State examinations and all, you might be getting a question simply like, what is the tolerance allowed in the voltage variation? What answer we have to give among these two? 6% we have to give, because we have to give that according to the Indian standards only. Okay. Universally speaking, it will be 5% variation was allowed in the voltage, but according to Indian standards, it will be 6%. What is the tolerance allowed in the frequency variation? Can anybody tell me? Tolerance allowed in the frequency variation. It will be plus or minus 1%. As a standard, it will be plus or minus 1%. But nowadays, the people are going even lower than this range. In order to have a good, what we call, tolerance is allowable variation. That's what I said. Tolerance is nothing but allowable variation. Yeah. So plus or minus 1%. According to the Indian system, standard frequency is of 50 Hertz, right? Standard frequency is of 50 Hertz. So 50 Hertz plus or minus 1% in the sense, frequency is allowed in the range of 49.5 to 50.5 Hertz. 49.5 to 50.5 Hertz. That's the range of the frequency variation accepted. Range of the frequency variation accepted. Yeah. Done? See, particularly AC transmission we are discussing. Let me tell you, we have many voltage levels like this, right? 11 kV, 33, 66, 110, 132, 220, 400, 765. Like this, we have many voltage levels. Okay. Which voltage level we have to select for the power transmission? Particularly, we are discussing about the transmission, transmitting the power. Okay. Which voltage level we have to select? Who will decide? Who will decide what voltage to be selected means? That will be decided by how much amount of power you are going to transmit. How much quantity, how many megawatts, or how much MVA amount of power you want to transmit. That you tell first. Next one, how much length you want to transmit the power. Means what the length of transmission line required, what is the distance of the power transmission. Okay, these are the two things which are going to decide which voltage level to be selected. Okay, so I'll write that simple statement here. Transmission voltage level selection. Transmission voltage level selection. Depends on, yeah, number one, amount of power to be transmitted, amount of power to be transmitted, power to be transmitted is one thing. Second one, distance of power transfer, or you can say length of transmission. Distance of power transfer, or you can call it as length of transmission line. Length of transmission. Yeah. Fine. Next thing. So I'm taking up a small example here to explain you little more about this voltage levels and all. Voltage level selection. Just a small example. Just go through it. See, this is one transmission line link we have with a reactance of X. Transmission line reactance is X, I am saying. Okay, just try to recall this formula. Try to recall this formula. I will discuss about this formula again in the power transfer equations in detail. Okay, but for time being, it is needed to us to continue the discussion. That's why I'm taking up here. See, sending end side voltage I am calling as mod Vs at an angle delta. Receiving end side voltage I am calling as mod Vr at an angle 0. Sending end side mod Vs at an angle delta. Receiving end side it is mod Vr at an angle 0. Line reactance is X. What is the expression for the real power transfer in the line? What is the expression for the real power flow in the line? Real power flow in the line. So P equals to, it will come like mod Vs into mod Vr, means sending end voltage magnitude into receiving end voltage magnitude by reactance of line, X you can say, into sine of angular difference between sending end voltage to receiving end voltage, it will be sine delta. So it will come like mod Vs into mod Vr by X into sine delta. Don't bother about this one. This is a very famous formula which will come many times in T&D as well as in power system analysis, as well as in the what we call alternators also, alternator study also. Okay, see, particularly the first mod Vs into mod Vr by X, mod Vs into mod Vr by X, you can call it as maximum power transfer capacity. You are naming that Vs into Vr by X as maximum power transfer capacity. So P equals to P max into sine delta. Okay, next thing. Next thing. So let's see. If length of transmission line was getting increased, what will happen? That's a study what we are going to take up in a simple way. If the length of transmission line was increased, definitely a series reactance of line is going to be increased. If length of transmission line was increased, series reactance value will be increased. X value is going to be increased. So if the series reactance value was increasing, what will happen to maximum power transfer capacity? You know, this maximum power transfer capacity was inversely proportional to reactance. So as if reactance is increasing, Pmax value will decrease. Maximum power transfer capacity value will be decreasing. Now let us take, as you know, P is equals to Pmax into sine delta. As you know, P is equals to Pmax into sine delta. Let me tell you this condition, very simple condition. This P value was constant. Means we decided how much amount of power we need to transmit. Let's say some 100 megawatt, 50 megawatt, some value we have fixed. Amount of real power to be transmitted was fixed. Okay, listen now, listen please. So after fixing that, if the length of transmission line was increased, X value was increasing, Pmax value decreasing. So this Pmax value was decreasing now because of length increment. P maximum value was decreasing. Okay, so Pmax is decreasing, but this product has to be maintained as constant. Means definitely sine delta should increase. Sine delta value should increase. So because of the sine delta increment, definitely it is expected that delta angle is going to be increased. Delta angle is going to be increased. Yeah, let me concentrate only on the final conclusion now. Let me concentrate only on the final conclusion. Simple. As if length of transmission line was increasing, maximum power transfer capacity was decreasing, and the angle delta, angle difference between the bus voltages, the angle difference between the bus voltages, delta, that is going to be increased. That is going to be increased. Because of this, what you can say is system stability, particularly the angular stability of system is going to be reduced. Okay, so I can say here system stability reduces. System stability is going to be reduced. System stability is going to be reduced. So because of increment in the length of line, system stability is going to be reduced for constant amount of real power transmission. See, listen. See, actually, the problem what we have to think here is simply, if you are using AC transmission line wire, you can't use that line for any length you want. They are using AC transmission line wire, you can't use that line for any length you want, because if the length is increasing, stability of system is going to be reduced. That's the problem. Okay, so that's why there will be some limitation on the length of the AC transmission line. That will be generally 500 kilometers according to standards. Okay, yeah, let me write that statement also here. With respect to stability of the system, system stability, AC transmission line length limited by 500 kilometers. Only for L less than 500 kilometers, we can use the AC transmission line. AC transmission line length will be limited by 500 kilometers. Okay, if it is needed to transfer the power for more than 500 kilometers, if it is required to transfer the power for more than 500 kilometers, what we have to do? We should go with the DC transmission line. Okay, so HVDC transmission. So therefore, you can say for length greater than 500 kilometers, HVDC transmission line can be used. HVDC line can be used. Length greater than 500 kilometers, we can go with the HVDC transmission line. HVDC line. Yeah, as a point comes now, can you please tell me what is the highest DC transmission voltage level in India? What is the highest DC transmission voltage level in India? Tell me please. Highest DC transmission voltage level in India. DC transmission voltage level in India. How much? So that will be plus or minus 800 kV. Plus or minus 800 kV. Plus or minus 800 kV. That's the highest DC transmission voltage level in India. See, actually, plus or minus 800 kV in the sense we have two wires here. One is a positive polarity conductor, 800 kV, and next one is a negative polarity conductor. It will be of minus 800 kV. Very simple. We have two wires, two paths also you can say, two wires like this. First wire is operating at plus 800 kV. Second wire is operating at minus 800 kV. That's the meaning of plus or minus 800. Okay, so you should not say conductor to conductor gap is 800. First conductor 800 positive, second conductor 800 negative. And this type of line we are going to call as bipolar line. Two polarities. One is a positive polarity conductor, Second one is a negative polarity conductor. We are going to name it as bipolar HVDC line. Bipolar HVDC line. Bipolar HVDC line. Okay. So definitely we'll get a shock. Is it AC or DC? Doesn't matter. You can say forward and return. No issue. Yeah. Next thing. Listen. See, from this point onwards, we will be concentrating only on the AC transmission voltage levels. From this point onwards, we are going to concentrate only on the AC transmission voltage levels. We are not going to discuss about the DC levels right now. Okay. Yeah. See, look at this DC transmission voltage levels here. 11, 33, 66, 110, 132, 220, 400, 75. Like that. At what voltage level you are generating the power? Can you tell me, please? At what voltage level we are going to generate the power? At 11 kV or maybe 13.2 kV, like that. We are going to generate the power. But as far as transmission is concerned, why you are looking for this much voltage levels? Why you are looking for this much voltage level like 220 kV, 400 kV, 75 kV? Why you are moving on to EHV and UHV levels for power transmission rather than transmitting the power at 11 kV itself? That's the question what we have to ask. So definitely, we will be getting certain advantages of using the EHV and UHV levels as compared to the normal high voltage level. That advantages we have to discuss now. Okay, so I'll say the heading in a clear way. Just observe the heading what I am writing. Look here. Advantages of using EHV and UHV levels compared to normal HV level in bulk power transmission. Not a small quantity of power. I am saying in the way of 200 megawatts or 200 MVA or 500 MVA, that much amount of bulk power if you want to transmit. We are moving on to EHV and UHV levels rather than the normal high voltage level. In that view, we are going to think about the advantages here. Okay, in transmitting bulk power, bulk amount of power. In transmitting the bulk amount of power. Okay. Advantages of using EHV and UHV levels in transmitting compared to HV level in transmitting bulk amount of power. Yeah, we have many advantages. Let me write the things. We will be transmitting power only, not voltage. We are transmitting power at a voltage level. That's it. Okay. See this. As you know, apparent power equation, three-phase. Three-phase apparent power. S is equals to √3 into line-to-line voltage multiplied with the line current. Only magnitudes. √3 into line-to-line voltage multiplied with the line current. Magnitude. Okay. Now, what is that line current magnitude here? S by √3 into line-to-line voltage. That's okay. S by √3 into line-to-line voltage. Okay. So first of all, already we said transmitting bulk amount of power. Transmitting bulk amount of power means S is a very, very large number. S is very large value. S value was very, very large. That's okay. Next thing. So after keeping that S value very, very large, for example, if I select VL value low, what will happen? Okay. If I select VL value high, what will happen? the comparison we are going to take up. Very simple. Okay. Normal HV. Normal HV level. Observe now, line to line voltage level is low value. Line to line voltage level is low value. See, for example, if this line to line voltage level is low, what will happen to IL value? What will happen to IL value now? S is very large, already we mentioned. S is very large, already we mentioned. But this VL is very low, and then IL will be very, very large, very high value. So line current is very, very high value to be expected in this particular case. Okay, next one. I will write here. EHV, UHV levels I am considering. Maybe 220 kV, 400 kV or 765 kV levels. How is a line to line voltage we are expecting high number? If that line to line voltage number is very high, definitely that IL comes to be very low. So line current will come to be very, very low. Line current will come to be very, very low. Okay, next. See, 1 minute, just listen carefully what I am saying. First comparison, what we are going to make here is in the view of the cost of the system. First comparison, what we are going to make here is in the view of the cost of the system. See, cost of transmission line means mainly we should think about two things now. Two things. One is a conductor cost. First one is a conductor cost. Second one is a insulation cost that we should not neglect. Two things we are saying now. First one is a conductor cost. Second one is a insulation cost. Clear? Now tell me please, in the first one, normal high voltage level, already we mentioned that line to line voltage is very low. Line to line voltage is very low. Then how is your insulation cost? If the line to line voltage is very low, how is your insulation cost? Insulation cost is low, but line current is very high, means conductor cost is high. Okay. So I'll write low insulation cost. You can write low insulation cost because of the low voltage level. But current is very high. So as you know, A is area of cross section is proportional to current rating. Area of cross section is proportional to current rating. On the basis of that, obviously area of cross section required will be high. Area of cross section required will be high. So conductor cost will be high. So area of cross section required is high. So conductor cost is high. Conductor cost is high, you can say. High. In the other case, what you can say, line to line voltage level is high. Means what? Insulation cost is high. High insulation cost. I will include tower cost and all after some time. High insulation cost. Insulation cost. But whereas this conductor current rating is less, means obviously area of cross section required will be low. Area of cross section is low means conductor cost is low. Conductor cost is low. Yeah, conductor cost is low. So these are the things we have to observe. Can you tell me now, based on this a small comparison what we have made, can you tell me which cost is low, which cost is high? Which cost is low and which cost is high? Means normal HV cost is high or low, or EHV cost is high or low. How you can say? We can't say it. Because if you are going for normal high voltage level, listen please. If you are going for normal high voltage level, insulation cost is less, but conductor cost is high. Whereas for EHV and UHV levels, insulation cost is very high, but conductor cost is low. Sum of the two is a resultant cost, right? Sum of the two is a resultant cost. So to avoid this ambiguity, I am going to take up some sort of graph. Look here. Next slide I am showing. Next slide. Just look here. See, this is a x-axis on which we are going to take up the voltage level. Voltage. On the y-axis, we are going to take up the cost of the system. Cost of the system, and cost in the sense you can write here conductor plus insulation insulation plus tower cost, and then transformer. Definitely step up transformer voltage rate will be different, transformer cost. And then we have circuit breaker, protection, all these things. Total we have to include on the y-axis. Total we have to include on the y-axis. Okay. So on the x-axis, I am taking x-axis, I am taking voltage level. X-axis, we are taking the voltage level. Yeah, just listen to my words, what I am saying. See, insulation in the sense, Ashish Raj, it is an insulation kept in between tower and conductor. Insulation means overhead line insulators is what we are keeping. That's the cost what we are discussing, not air. Yeah, listen here. Listen. See, as and when operating voltage level is getting increased, overall cost of the system, overall cost of the system definitely starts decrease. But that decrement, what you are saying now, it won't happen for complete increment in the voltage. Maybe like this, you can say. Cost of the system will start decrease like this. Up to certain level, it will go. Beyond some voltage level, cost of the system will start increase because of excessive rise in the insulation cost. Like this, we can expect the cost versus voltage curve. All of you getting this? All of you getting this one? Does insulation compared with metal? We are comparing cost only. We are not comparing the electrical characteristics of an insulator and a metal. We are comparing only cost of insulator and cost of metal. That's it. Yeah. Look here. See, this graph what we are plotting now, it is for constant S value, apparent power, constant S, and fixed length of transmission line. For these conditions only, we are taking up this plot. Okay, now next thing, kindly observe here. This is the lowest cost of system of a given system to be expected. Yes or no? This is the lowest cost of the system to be expected, and this is the optimum voltage level. Optimum voltage level means the meaning of this statement is, yeah, already we have taken a fixed length here. Yeah, listen please. The meaning of the statement is, if you select your transmission voltage level very close to the optimum, then definitely we can expect that the overall cost of transmission is very, very low. Okay, next thing. Listen my words, please. Don't confuse. Very simple. Till now, what we have discussed in this comparison, I will recall once again. Just look here. Just I have taken the apparent power formula. Current formula I have written. Normal high voltage level. Line to line voltage level is low. So current is very high. Insulation cost is low. Conductor cost is high. EHV. Voltage level is high. So definitely current is low. So insulation cost is high. Conductor cost is low. Now we are going to take up the overall cost versus voltage level. Like this we got overall cost versus voltage level. Now the thing what I am saying is, particularly if the bulk amount of power transmission we are discussing, this V optimum value will come very, very high. It will fall in the category of the EHV and the UHV levels. That's why we can say EHV and UHV levels are economical compared to normal high voltage level for bulk amount of power transmission. Okay, so if you want, I will write the statement. It's a very simple one. V optimum comes in the range of EHV and UHV levels UHV levels for bulk power transmission. Bulk power transmission. So these levels are economical. These levels are economical in bulk power transmission. In the bulk power transmission. These levels are economical in the bulk power transmission. So cost is increasing beyond V optimum. Why it is so means because of increment in the installation cost heavily compared to decrement in the conductor cost. So actually one cost is decreasing, other cost is increasing. That summation is the resultant cost. So overall cost after summing up is decreasing up to V optimum. Beyond that it is increasing in the sense increment in the insulation cost is dominating the decrement in the conductor cost. Increment in the insulation cost is dominating the decrement in the conductor cost. That's why the overall cost is increasing, we can say. Okay, yeah. So this is one of the advantage you can call is a number one. You can say advantage number one. Yeah, let me think about the second advantage now. Second advantage. Yeah, anybody tell me what is the expression for the power loss? What's the expression for power loss? Three-phase power loss. Power loss, three-phase. So P loss you can say, which is 3 times of current square into resistance value. 3 times of current square into resistance value. Okay, 3 times of current square into resistance value. But you see here, at what stage we are discussing this problem? Is it at designing or operating? At what stage we are discussing this thing? Designing or operating? We are discussing this in the designing stage only, not in the operation. Yeah, not in the operating. We are discussing this in the designing stage. Okay. In the designing stage, we are selecting voltage level. We are selecting the voltage level. According to selection of voltage level, current rating will change. According to change in the current rating, we have to modify area of cross section. So I can say that I proportional to area of cross section, in the sense definitely I square proportional to A square, you can say. Not only that, whenever you are varying the area of cross section of conductor, definitely resistance value also changes. Resistance value also changes. So you can say R is inversely proportional to area of cross section. So now you can take up the power loss relationship with respect to area. Power loss relation with respect to area in the design stage. So power loss proportional to I square. I square in the sense you can write A square and you have R in the sense 1 by A. So power loss will be proportional to area of cross section. Power loss will be proportional to area of cross section. For what condition? For constant amount of power transmission at the design stage. For constant power transmission at designing stage. Designing stage. For constant amount of power transmission at the designing stage. See, as far as VHV and UHV levels are concerned, definitely area of cross section is decreasing. That's what we have mentioned here. Yes or no? Area of cross section is decreasing if you are going for EHV and UHV levels. Because of decrement in the area, obviously power loss is going to be decreased, right? So as area is decreasing in bracket for EHV and UHV levels, definitely power loss is decreasing. So if the power loss is decreasing, definitely you can expect that the efficiency of system increases. Efficiency of the system is going to be increased, we can say. Efficiency increases. Yeah, next thing. So next advantage I will take up. Next advantage, third one. Third advantage. See, already we said one comment. We said one comment that with respect to increment in the length of line, something like this. Yeah. Look here, look here. If length of line is increasing, X is increasing, maximum power transfer capacity is decreasing, and we can say stability of system is going to be reduced. But if you are going for EHV and UHV levels like this, EHV and UHV levels, definitely, this product VS into VR is going to be increased, right? Operating voltage level is increasing means definitely this product VS into VR is going to be increased. Because of the Pmax is going to be increased. Because of increment in the P maximum, definitely the system stability is going to be improved. Okay, so that is also one of the great advantage of using the EHV and UHV levels, right? So maximum power transfer capacity, you can write Pmax. Formula will be sending end voltage magnitude into receiving end voltage magnitude by reactance of line. So because of EHV and UHV levels, VS is increasing, VR is increasing, Pmax increases. So right for EHV and EHV comma UHV levels, maximum power transfer capacity will be definitely increased. So stability of the system will be more if you are going for EHV and UHV levels. So these are some specific advantages, what you should say. Overall cost of system will be a bit low. Okay. Next one, we are saying power loss is decreasing, efficiency increases. And maximum power transfer capacity of system is increasing means stability of system is going to be improved. Any disadvantage we have? Any disadvantages of using EHV and UHV levels? Anybody? Any disadvantage of using EHV and UHV levels? See, as and when the operating voltage level is increasing, definitely the electric field intensity on the surface of conductor is increasing. If electric field intensity is getting increased, definitely possibility of getting corona will be more if you are going for EHV and UHV levels as compared to normal high voltage levels. Okay, yeah. So I can say here disadvantage of EHV comma UHV levels will be corona increases. Corona increases. Okay, done. Next thing. So next, what we are going to discuss mainly is some problems. Some problems in the sense, what will happen to area of cross section of conductor if the voltage level is increasing by number of times. Okay, that type of problems we are going to discuss. Means relation between voltage with respect to size of the conductor. Voltage with respect to size of the conductor. At what stage? Designing stage only we are saying. Okay, fine. Next, before moving to that, I want to define these two terms, which will come frequently in our study further and further. One is a definition of a feeder. Next one is the definition of a distributor. These two things we'll discuss first. Later on, we'll move on to some problems. Yeah. So let's move to the next slide. To define the first term, what I said now, that is feeder. Definition of a feeder. Yeah. See, actually, feeder is nothing but a conductor. Which is going to carry constant amount of current throughout the length. Let me write. It's a conductor. Carries constant amount of current. Throughout the length. Else you can say constant current density at all places. Constant current density at all places. constant J. J. What's the J formula? Current by area of cross section. J formula, it is current by area of cross section, you can say. Constant current density. Current by area of cross section. Okay, so I'll try to explain about this term feeder by taking some small example. Taking a small example. Just look here, look here. This is one power generator we have. With a rated voltage of 11 kV, you assume. We have a generator of 11 kV rated voltage. At a distance, at a far distance, I can say, we have one 220 kV grid. We have a 220 kV grid. Okay. Now, listen please. Listen please. I want to interconnect. This 11 kV generator bus to the 220 kV grid. I want to interconnect this 11 kV generator to this 220 kV grid. How? How in the sense, definitely, first I should use a step-up transformer of 11 kV by 220 kV. Then we have to run a 220 kV transmission line wire and we have to connect that to the 220 kV bus bar. That's the connection what you have to make. So I can say first here, we'll keep one transformer of 11 kV by 220 kV, 11 kV by 220 kV, and then we are going to run a 220 kV transmission line wire connecting to this 220 kV grid. 220 kV line connecting to the grid. 11 kV by 220 kV transformer. Step-up transformer, you can see. Step-up transformer. Simple. Next, listen please. Very simple question. Very simple question I am asking you. See, can I say this 220 kV line is going to carry same amount of current throughout its length? For example, if the input current is I here, what is the output current of this line? What's the output current of this line? Will it be same number? Yes or no? Yes, definitely. Nobody is responding. Because there are no tappings, right? We don't have any tappings on this wire. We are not tapping any current or power from this wire at any place. So the input current and output current of this wire will be same. So current throughout the length of this transmission line will be same. So can we call this line as a feeder? Can we call this line as a feeder? Yes or no? Yes. So this line can be called as feeder, right? So simply what I can say is, yeah, Salman Khan, you asked me your doubt in doubt session once. Yeah. So simply what I can say is, the best example for feeder is a transmission line wire. Best example for feeder is transmission line wire. So example for feeder is transmission line wire. Transmission line wire, which is going to carry constant amount of current. Constant amount of current throughout the length. Okay, losses will be there. Why you are bothering about losses? I'm not saying power is equal. I'm not saying input power and output powers are equal. I'm saying only current. Talking about only current. Current variation is negligibly small throughout the length. So, moreover, we are not keeping any tappings. No tappings on transmission line. Because no tappings on transmission line wire. No tappings on transmission line wire. And so obviously the transmission line can be treated as feeder. Now, next thing. Please listen. On what basis we will select the size of this conductor? On what basis we will be selecting the size of this 220 kV line conductor? Means that is generally on the basis of the current rating. Right? Based on the current rating, we are going to select the size of the conductor. Let me write in the next slide. Feeder size. Selected on the basis of current rating, you can say current rating or sometimes you can say current density. Sometimes you can say current density or every transmission line is going to be called as feeder only. That's what I am saying now. Every transmission line is going to be called as feeder. See, very simple. On the transmission line or any wire, you don't take any tapping. You don't take any tapping, that is going to be called as simply feeder. Okay, next. I'll discuss about distributor. Why you are hurrying? We'll discuss about distributor. Current density, or sometimes you can say it is based on the thermal limit of the conductor. Thermal limit of the conductor. Thermal limit means simply it is a temperature, or you can say current level, or you can say power beyond which conductor may get melt down. Conductor may get melt down. So I can say thermal limit. Thermal limit. So who is going to decide the heat in the conductor? Power loss. Power loss is a term which is going to decide the amount of heat generated. So I can say I square R loss is one of the criteria on the basis of which we are going to decide the feeder conductor size. Feeder size. Yeah, next. So before moving on to distributor, let me make some comment on this transformer. I think most of you might have studied this in your transformers course. Transformers course. Yeah, just listen to me. Just listen to me. It's a step-up transformer, right? 11 kV by 220 kV. It's a step-up transformer. What's the connection we suggest for it? What's the connection we suggest for this one? Connection. Connection, it will be generally delta star ground. Economical connection. Listen please. Economical connection suggested for step up. Step up is delta star ground. Whereas for step down, reverse, star ground delta is suggested, particularly in the transmission system, not in the distribution. Not in the distribution. Only in the transmission system we are going to take up that comment. Yeah. So let's move. I'll write in the next slide. In the transmission system, delta star ground is used for step up application. Star ground delta is used for step down application. These are economical connections. Economical connections. Economical connections. Okay. Yeah. So next we will be moving on to the definition of distributor. We are moving on to the distributor. Next slide. Distributor. See, this term distributor is quite different from the other. Yeah, how in a sense, just you might have studied in transformer. I can't repeat all the things what you have studied in other subjects. Okay. Just if you have any doubt, you ask me in the doubt session. It's better. Okay. I can't explain now how. You ask me in doubt session once. Yeah. Kindly listen. Distributor. It is just a different from feeder. What you can say is simply, for example, you say in a practical case, if a distribution line entering into our area, we used to take tappings from the wire. After taking the tapping, definitely current will be different from one location to other location on the wire. That why we are going to name as distributor simply. So it's a conductor. It's a conductor which have a different value of current with respect to length. Okay. So it's a conductor. It's a conductor having variable amount of current flow. Variable amount of current flow. Current flow throughout the length. Throughout the length. Variable amount of current flow throughout the length. Yeah. See, means obviously we used to keep number of tappings on the wires, right? So I can say tappings are taken at various places. Tappings are taken at various places. Various places. Or else you can say variable current density also. Current density will be different from one place to other place on this wire. Okay. J, current density is different from one place to other place. So you can write this as a variable current density with respect to length. With respect to length. Okay, now I will be taking up these two terms, so-called feeder and distributor, in the view of a distribution system. So I'll show a practical distribution system. In that, what's the feeder location and what the distributor location? The small, what we call discussion we are going to take up in a practical distribution system. Okay, as an example. As an example. So I'm moving to the next slide to take up that example. Just look here. Example. Just listen to this. See, this is one transformer, maybe substation you can feel. Substation transformer. Substation transformer. Level 33 kV by 11 kV. Generally, the substation what you see outside. Distribution substation we call, not distribution transformer. It's not distribution transformer. I'm saying distribution substation. Distribution substation. 33 kV primary voltage level and 11 kV is a secondary voltage level. Okay. See, from this 11 kV bus bar, number of lines will run out. Maybe this is one 11 kV wire running out, second 11 kV, third, like this number of 11 kV wires will be running out in this manner. And each and every 11 kV circuit, you can call it 11 kV circuit, is supplying power to some distribution area. Supplying power to some distribution area. Okay, so let me show that. For example, the first one is supplying power to some distribution area like this. And the third one is supplying to some area. And fourth one is also supplying power to some area. So second one we have to concentrate mainly. Yeah, look here. Second 11 kV feeder running in this manner. For example, just listen. This 11 kV circuit is entering into some village, or entering into some area. And what the people will do simply is, they will take a tapping from this wire. Maybe something like this will take a tapping. So after taking the tapping, they will connect this to a distribution transformer. Distribution transformer, DTR. Distribution transformer. See, listen. This distribution transformer might have 11 kV level in the upper side, 11 kV side. Bottom side, it may be 415 volts, or sometimes, as somebody is asking me, it might be 400 volts sometime, or 440 volts sometime. That depends. Okay, so 11 kV by 415 volts, and it's the low voltage now. Upper one is a high voltage, bottom one is obviously low voltage. And this low voltage, from this low voltage, wires will be running in the street on the pole. Distribution lines. Like this, we can expect number of lines. On these lines, we take tappings and supplying number of domestic loads. Okay, houses will be connected. So maybe like this, we can say number of houses are connected to this one. Number of houses will be connected to this in this manner. So it's a distribution load, domestic load or distribution load, domestic. Okay, will this 11 kV wire will stop here or will continue to run? Whether that 11 kV wire stops there or continue to run. It's a three-phase transformer, definitely. Isn't this? Will this 11 kV wire stops here or continue to run? Definitely continue to run. Beyond some distance, beyond some length of this 11 kV wire, definitely we take one more tapping and one more distribution transformer is connected and a similar type of load is getting connected here. I'm showing simply as a load, but it's a load of this kind, this type. And again, after some more distance, one more distribution transformer we can expect and some more load is connected to that. Like that, as we progress further and further, number of distribution transformers are connected along with their loads. Number of distribution transformers are connected along with their loads. So this is one of the very practical distribution system in India. Very practical distribution system in India. Okay, so it's a practical distribution system in India. Distribution system in India. Yeah, one more thing what I want to say here is, listen please. Listen please. All these transformers what I have shown here, including substation transformer, remaining all distribution transformers, these are a delta star ground only. What's the type? Is it step up or step down? How are these transformers we have in the system? Step up or step down? Step down. Definitely in the distribution system, lower side of system, always whatever the transformers we have, these are step down only, step down. See, according to the economical view, what connection we should use for step down? We have to go for star grounded delta. But as a special case, in the distribution system, we have to go with always delta star ground transformer. Delta star ground transformer. Okay. All the time, we should go for delta star ground transformer. So if you want, you write it. Write that statement if you want. In distribution system, always delta star ground transformers are used. Even though those are of step down in nature. Step down in nature. Even though those transformers are of step down in nature, we are going with the obviously so that loads to houses receive different power. See, Charan, how much amount of power you are going to draw, that depends upon your load. Whatever the load you connect, that will that much amount of power will be supplied with a nearby transformer or distributor or whatever it is. Okay. See, supplier will not decide how much amount of power you want. Supplier, distribution company will not decide how much amount of power the house is required. House is demanding the power. According to the demand, the supplier should supply. The company should supply. Okay. Yeah. So let's move. Listen to this diagram. Listen to this diagram once. See, I am starting from this 11 kV bus bar to the point of the first step. 11 kV bus bar to the point of first step. Is there any change in this current? In that particular red color wire, what I have shown, can I say the incoming current and outgoing currents are exactly equal? Incoming current and outgoing currents are exactly equal. Yes or no? Yes. So can we call this as a feeder? Yes. This we are going to call as feeder. Yeah, kindly, Charan, and many of you are having this very silly doubt. Just listen to me. Voltage may be same for each and every house, but power demand is different. What is power? Voltage into current into power factor. How much amount of load you connect? Based on that, you will be drawing the power. Voltage is same for each and every house, right? Yeah. Listen here. So this is a feeder. This is a location of feeder, what you can see. Starting from this terminal, some current is drawn by this load. Okay. Remaining current will go out. Let's say this current is I. And this current will come to be I1, which is definitely less than I. And in that I1, again, some current is drawn by this load. Remaining current will go like this. That's I2. I2 is going like this. Some current is drawn by the load. Remaining current, you can say I2. Like that, what you can say is, the current flow in this wire is continuously changing. Current flow in this wire is continuously changing. With respect to length, what we call this blue color line now, it's going to be called as distributor. It's going to be called as distributor. Okay. Even it is in step down nature. All the transformers what we are using in the distribution system are step down. Step down. Economical connection is star ground delta, but still we are using delta star ground. That's the thing you have to identify kindly. Okay. Yeah. See what we call this portion. Can anybody tell me what we call this one? Can we call this also as a distributor? Yes, definitely, because current is changing with respect to length, and this can also be called as a distributor. But voltage levels are different. Voltage levels are different. You know, the upper distributor is operating at a voltage level of 11 kV. You can call it as HV distributor. Lower distributor is operating at low level of what we call 415 volts. You can call it as LV distributor. HV distributor and LV distributor, or you can say secondary distributor. Bottom one is the secondary, top one is a primary. Like that also you can discriminate these two. Yeah, I will show the distributor slide. Please complete it if you are writing. Please complete this one. Yeah, one of the reasons you can say to access a neutral wire, in order to access a neutral wire, so definitely we have to provide that star ground on the secondary side. Okay. Yeah. So let's continue. Listen here. So I'm showing previous slide. If anybody is still writing, please complete this one. Distributor slide. Somebody asked. Why full 11 kV line is not a distributor? Navdeep, I said already, some portion is carrying constant current, remaining portion is carrying variable current. Up to the point where we have a constant current flow throughout the length, it's called as feeder. Beyond that point, we are going to name it as distributor, because current is changing with respect to length. Yeah, correct, Madhu Chandra. Neutral is grounded. I'll come to your doubt regarding transformer. Please wait. Look here once. Regarding distributor, I'm talking a little bit regarding the distributor. Listen, please. See, for example, if it is section number one, we have some voltage drop in this section. Definitely, we have some voltage drop in this section, and obviously the load is experiencing some voltage. And again, we have some voltage drop in the second section also. This load will experience some voltage. For example, in a simple way of analyzing, If the voltage drops in the distributor sections are more or high. If the voltage drops in the distributor sections are high, then definitely the loads will experience a low voltage. Loads will experience a low voltage means obviously we can say performance of load may not be satisfactory. Listen to my words, please. Listen to my words, please. If the voltage drops in the distributor sections are large, definitely the loads will experience low voltage. Because of that, the performance of the load may not be satisfactory. So to overcome this issue, you try to select the distributor size. Try to select the distributor size on the basis of voltage drop only, such that voltage drop is getting minimized and we have a good voltage profile for the load. That is a designing criteria for the distributor. Okay, so I think most of you have understood the statements what I said. Let me write it. Let me write it what I said now. Just listen. Okay. To maintain good voltage profile at load, good voltage profile at load, loads, the voltage drop in the distributor must be low. Voltage drop in the distributor must be low. Must be low. So the distributor will be designed on the basis of voltage drop criteria. Distributor will be designed on the basis of voltage drop criteria. Voltage drop criteria. So the distributor will be designed on the basis of voltage drop criteria. Okay. So why you are not considering this voltage drop criteria in case of feeder? Can't we have voltage drop in the feeder? Why you are not calling this voltage drop criteria in the feeder? Sorry, in the transmission line, or you can say feeder. Can't we have that voltage drop in the feeder? See, definitely you have a voltage drop. No tapping, so no drop. It's not the thing, Imtiaz or Alan. Just listen what I am saying to you. See, any conductor carrying some current having some impedance. Any conductor, either it is a distributor or feeder. Those are the names what we have given. After all, if you think about a conductor outside, if it's carrying some current, having some impedance, definitely we have a voltage drop in that. There is no doubt about it. So we have a voltage drop in the feeder as well as we have a voltage drop in the distributor, both. But in case of feeder, even though you have a voltage drop, it is possible to maintain a good voltage profile by means of the compensators. By means of the compensators, it is possible to maintain a good voltage profile for the feeder. But keeping those compensators or controllers may not be economical in the distribution system. That's why at the design stage itself, you take care of that voltage drop by selecting the conductor size. So called the distributor size. I think all of you getting my point. Yeah. Tell me please. All of you getting my point? So I'll write here. So the distributor will be designed on the basis of voltage drop criteria. In bracket you write. So keeping compensators is not economical in distribution system. That's the reason why we are moving on to the voltage drop criteria. Yeah. Yes. Yeah, load. See, actually, current rating also going to be considered definitely. We have two things. One is voltage drop criteria. Next one is a current rating. Primary criteria, it's a voltage drop. Secondary criteria, current rating. So definitely current rating has to be satisfied. Along with the current rating, we are saying one more criteria as a voltage drop. But voltage drop criteria should be given more preference as compared to the current rating. Current rating must be satisfied. Examples of these compensators, simply it's a shunt capacitor bank and all. Okay, fine. So these are the definitions of the fader and distributor. Fader and distributor. So have a break for 10 minutes. After break, I will be discussing about some problems in this area. Okay, 10 minutes break. 10 minutes break. We'll meet after 10 minutes and we'll continue with some problems. Yeah. So I have resumed audio video on screen. So kindly go through this question. For same power transfer and same efficiency, if operating voltage of transmission line is increased by n times, then the area of cross section of conductor is reduced by dash number of times. That's a meaning. Okay. So please kindly respond. Please raise your hands. Yeah. So let's continue with this problem. See, we have some conditions here. We have some conditions. First condition is same power transfer. Constant amount of power flow. That's the meaning. Okay. Same efficiency means same efficiency, even the voltage is getting increased. Voltage is going to be increased by n number of times. What is the area of cross section of conductor? Means what will happen to area of cross section of conductor? It is going to be reduced by how many number of times? That's the thing. See, we have to consider this problem in two cases now. Case 1, without increasing the voltage. Case 2, after increasing the voltage. Let us say case 1. Case number 1. Without increasing the voltage, we have voltage as V1. Case 2. After increasing the voltage, we have the voltage as V2. Okay. See, as and when you are changing this voltage levels at the designing stage, particularly, definitely what we call conductor current rating also going to be changed. Conductor area of cross section is also going to be changed. So let's say current rating here is I1. Current rating here it is I2. So just now we said voltage V2 equals to N into V1. Voltage was increased by N times now. So V2 equals to N into V1. So I can write V2 by V1 is equals to N. This is one relationship. V2 by V1 is equals to N, you can say. Okay, next thing. Same power transfer condition, let me take. Same power transfer means you consider it as real power. Real power. In the case 1, per phase analysis you take, per phase. Case 1, V1 I1 cos phi 1. Case 2, V2 I2 cos phi. These two we should make it equal. So I'll say in the next slide, P1 is equals to V1 I1 cos phi 1. It's a case 1 power. P2 equal to V2 I2 cos phi 2. P1 I1 cos phi 1, and then we have V2 I2 cos phi 2. Next thing. Listen, please, listen. Already we said just now, same power transfer in the sense. The question here is, who is going to decide the amount of power flow? Who is going to decide the amount of power flow? Obviously, load. Obviously, load kept at the receiving end side. See, same amount of power transmission in the sense, can we expect that load remains same? Load will be remains same in both cases. If the load remains same in both cases, definitely power factor cos phi 1, cos phi 2 will be approximately equal. That's the assumption what we are making now. Okay, so I am writing the statement for same power transfer, comma, same load kept at the end, same load kept at the end. Okay, so therefore power factors cos phi 2 and cos phi 1 are approximately equal. Power factors cos phi 2 and cos phi 1 are approximately equal. Okay, so as we said already, powers P2 and P1 are equal. I can call now V2 I2 equals to V1 I1. Cos phi 1, cos phi 2 will be cancelled out. Cos phi 2, cos phi 1 will be cancelled out. So you can get here V2 I2 equals to V1 I1. See, from this, current I2 will come to be V1 by V2 into I1. V1 by V2 into I1. What is that value V1 by V2? What is that value V1 by V2 here? 1 by N. V1 by V2 equals to 1 by N. So I can say current I2 equals to 1 by N into I1. 1 by n into I1. This is a relationship between the currents I1 and I2. I2 equals to 1 by n into I1. Clear? Next. First condition we satisfied. Same power transfer condition we satisfied. What's the second condition left in the problem? Same efficiency. Same efficiency condition we have to satisfy. Same efficiency. See, first of all, what is the formula for efficiency? What is the formula for the efficiency? Very simple. It's output power by input power. Output power by input power in the sense, you can say it is output power by input power is output power plus power loss. Output power by output power plus power loss, you can say. So it's a AC transmission line only. Unless otherwise, if we mention that as DC, we should consider it as DC Vishnu. Else we should consider it as AC transmission line only. Okay, kindly listen to me. Kindly listen to me. Already we said same efficiency. Same efficiency. That's okay. And we said same power transfer also. Same power transfer also. See, same power transfer means can we expect the output power remains same in both cases? Can we expect that output power will be remain same in both cases? Yes or no? Yes, definitely. So if the output power is same in both cases, as well as we are saying that efficiency also same, then definitely power loss must be remain same in both cases. If you want to write efficiency 1, power loss 1. Efficiency 2 is same output power by same output power plus power loss 2. So as efficiency 1 and 2 are equal, efficiency 1 and 2 are equal, definitely you can call power loss in the case 1 and power loss in the case 2 must be equal. Power loss in the case 1 and power loss in the case 2 must be equal. Okay. What is power loss formula now? What is the power loss formula? I square into R. Power loss formula will be I square into R. Getting me? I square into R. So you can write this one simply I1 square into R1 power loss. And here you can call it is I2 square into R2 power loss. I1 square R1, I2 square R2 per phase. 3 may be cancelled if you want. Okay. Now you can have this resistance R2 value will come to be R1 into, you take this I2 to the other side. So you can get this like I1 by I2 whole square. I1 by I2 whole square. What is that value I1 by I2? I1 by I2 is equals to N. You can get from this. I1 by I2 value will come to be N. So it will come like R2 is equals to N square into R1. R2 is equals to N square into R1. And R2 you can write rho L by area of cross section A2. R1, rho L by area of cross section A1. From that you can get the comparison between A1 and A2 areas. Yeah. So you can get here rho L by A2 N square into rho L by A1. So rho L will be cancelled out. So 1 by A2 is equals to N square into 1 by A1. 1 by A2 is equals to N square into 1 by A1. So from this you can get area of cross section A2. Yeah, please complete it quickly. I'll move to next slide. Yeah, so I can write from this now. A2 will come to be 1 by N square into A1 area. A2 is equals to 1 by N square into A1. So I can say area of cross section is reduced by how many times now? Area of cross section will be reduced by how many times? Tell me please. It will be reduced by N square times. So I can say from this the conclusion is area of cross section was reduced by N square times. It will be reduced by N square times. Yeah, clear. So I'm showing previous slides. Please kindly complete. 43F I am showing. Complete it quickly. If you are still writing. 43F. Then just before slide 44. Yeah. So next, let's repeat the same question in a different mode. I'm repeating the same question in different mode. Kindly observe. Okay. For same power transfer, that's it. We don't have this condition of same efficiency. This is a question. See, for same power transfer, if the operating voltage of transmission line is increased by n times, then the area of cross section of conductor reduced by dash. Area of cross section of conductor reduced by dash. Yeah, kindly observe now. So almost same problem, na? Earlier we have taken case 1 V1 I1, case 2 V2 I2. Let me look into this problem else. Okay, V1 I1, V2 I2, voltage is increased by n times, V2 by V1 equals to n. Okay. Next, same power transfer, same conditions, I2 equals to 1 by n into I1. Up to this point, it is same. Up to this point, it is same. But you don't have a condition of same efficiency, so I can't do this slide at all. So I can say as a conclusion directly, V2 is equals to n into V1. Voltage is increased by n times. Current will become 1 by n into I1. Why it is so means? Same power transmission. Same power transmission. And now you don't have a condition of same efficiency. We don't have a condition of the same efficiency. Now, listen please. Listen the rule. Listen to the rule here. First attempt, we should try to satisfy all the conditions whatever given in the problem. You should consider all the conditions given in the problem and you should make an attempt to solve the problem. If it is not possible still, like this we got some result like I2 equals to 1 by n into I1. I don't have any other condition in the problem. I don't have any other condition in the problem. We stop at this point. But now I have to get the relationship between the areas. For that purpose, you can make any assumption. You can make some assumption and write that assumption and try to give the answer according to the assumption what you have considered. Okay. See, many times we use it to say current is proportional to area of cross section. Many times. Yeah. Many times we know current is proportional to area of cross section. But strictly speaking, look here once. Look here. So current is proportional to area of cross section means what is it proportionality constant? What is it proportionality constant? Current is equals to J into area. Current is equals to J into area. J, current density is a proportionality constant. Yes or no? Clear? So I should say I2 is equals to J2 into A2. One formula. I1 is equals to J1 into A1. Another formula. Now we have to substitute these two into current relationship. So I2. So J2 into A2 equal to 1 by n into I1. I1 is J1 into A1. J1 into A1. But the condition what we are going to consider now, or the assumption what we are going to make now is J1 and J2 are equal. That's assumption. Means constant current density we will assume. Then we can get the relationship between the areas. Okay. So assuming that J2 is equals to J1, same current density. Okay. So you can have A2 is equals to 1 by n into A1. A2 equals to 1 by n into A1. So from this you can say area of cross section was reduced by how many times? N times. Area of cross section reduced by n times. A small change of removing the condition of efficiency, we got this result. Yeah. Done. So let's take one more problem. One more problem in this. So go to this one. It's a previous ESE examination question. Objective exam. Yeah, go through it. If a fixed amount of power to be transmitted over certain length with fixed power loss. Look at all the conditions what they have given in the starting two lines. It can be said that volume of the conductor is, some options are there. Option A, inversely proportional to magnitude of voltage and that of power factor of load. B, inversely proportional to square of the voltage and square of the power factor of the load. C, proportional to square of the voltage and that of power factor of load. Proportional to magnitude of voltage only. So he is asking a relationship between voltage and power factors. Volume of the conductor to voltage and the power factor. That relationship we have to get. Okay. Let's proceed with the starting lines, what they have said. Starting lines. Just observe. First line. Fixed amount of power to be transmitted. Means real power flow is constant. Real power flow is constant. What is the formula for real power flow? You take per phase only. You take per phase. What is the formula? V into I cos phi. And he's saying that this power flow is constant number. Power flow is a constant number. To be transmitted over certain length. Means length of transmission line is also constant now. Length of transmission line is fixed value. L. Length of transmission line is constant. Next, fixed power loss. What's the power loss formula? I square into R. Current square into resistance, you know. Power loss. Current square into resistance. And this power loss is also constant, what is it? Power loss is also constant. Now, he is asking us to give the relationship between volume of the conductor to the voltage magnitude and the power factor. Okay. What is volume of the conductor formula? Volume of conductor formula. Tell me anybody. Simple thing. What's the formula for volume? So it will be area of cross section of conductor multiplied by length. Area of cross section of conductor multiplied by length. So I can write this one A into L. That's it. So already length is constant, he said, na? Length is constant. Now we should think about area of cross section formula. How to get area of cross section formula from these things? How to get the area of cross section formula from these things? Already you know resistance rho L by A, rho L by A. From that we try to get the area formula. Okay, but you have current, right? How to get that current? That current we can get from the power equation. That current we get from the power equation. All of you getting this one? So I'll write in the next slide. Power loss equals to I square into R. So you can say this is I square into resistance is rho L by A. So area of cross section will be I square into rho L by power loss. Okay. So as we know, real power transfer is VI cos phi. You can write current from this. P by V into cos phi. Like this you can write. Current is equals to P by V into cos phi. That you dump into the current term in the area of cross section. So area of cross section equals to P by V into cos phi whole square into rho L by power loss. Clear? Now, volume of conductor if you write, volume of conductor A into L. A into L means you can write this like P square by V square cos square pi into rho L square by power loss. Rho L square by power loss. I think all of you getting this? Clear? Okay, now you can see in this term, power constant value. Resistivity also constant for a material given. Length is also constant. Power loss is also constant. From this, you can say simply, volume will be inversely proportional to square of the voltage magnitude and then square of the power factor. Volume will be inversely proportional to square of the voltage magnitude and square of the power factor. What option is the suitable one here? What option is suitable? Option B is a suitable one to be considered. Inversely proportional to square of the voltage and square of the power factor of the load. So I can say the correct answer from these things will be B. Correct answer will be B. Okay, done. So this type of problems we used to get in the examinations. Just go through the previous GATE questions again. Hardly 1 or 2 questions you can find in this manner in the GATE. In the whole history of GATE, only 1 or 2 questions of this kind relating area, voltage, and all. Okay. Yeah. So next topic what we are going to discuss in this chapter is types of conductors. What are the different types of power conductors? Classification. What will happen if they have asked only for area? That's also same answer, right, Sridhar? Same answer, no? 1 by voltage square into cos square pi. That's the same answer. Yeah. So let's move to the next slide. Types of power conductors are simply write types of conductors. Types of conductors. Yeah, check this. So what are the different types of conductors to be expected? Once again, volume inversely proportional to how, as real power is constant. Bindu, go through that once again, Bindu, what I said. Volume equation we have found ultimately here. After finding the volume equation, we came to know this power is constant in this volume equation. P is constant, rho L square constant, power loss is constant. He is asking relation between volume and voltage and power factor. So volume will be inversely proportional to voltage square into power factor square. That's it. Yeah, types of conductors. First conductor we can say is a solid conductor. First one. Yeah, I am opening the question. Somebody is asking. Go through the question once. Already, we have uploaded that classroom practice questions in the website in the student portal. Please download it, take a printout, be ready with that while you are attending the class. Okay, you can get the questions from that what we call file only. Okay. So first conductor we can say it's a solid conductor. First one, solid conductor, or you can call this one as a single strand conductor. Single strand conductor. Solid conductor, or you can say single strand conductor. Second one. Homogeneous stranded conductor. Homogeneous stranded conductor. Homogeneous stranded conductor. Third one, composite stranded conductor. Composite stranded conductor. Stranded conductor. Homogeneous stranded. Next one is a composite stranded. Fourth one, you can say bundle conductors, or you can call multi-conductor system. Bundle conductors, or you can say multi-conductor system. Multi-conductor system. Simple. In each and every phase, we used to keep 2 or more number of conductors. 2 or more number of conductors. Yeah, I will check that, Ramakrishna. I'll check it once. Yeah, bundle conductors, or you can say multi-conductor system. Next, fifth one, you can say hollow conductors. Hollow conductors. These are the 5 types of conductors to be expected. See, before moving on to any type of conductor here, first what we should know is how should be the shape of the conductor. Most of the times you might have seen outside different conductors, and how should be the shape of conductor, or what the shape of conductor you have seen? Circular. Most of the times you will see circular shape of conductor only. Why you are moving on to circular shape of conductor? Why can't we take up a square conductor, a rectangle shape as a bar? Okay, so that's the thing we have to discuss. Yeah, for example, we have 2 conductors here. One is of a circular shape, right? One is of circular shape, and second conductor is of a square shape like this. Okay, so circular conductor is one thing. It's a square shape conductor as a second one. Square shape conductor as a second one. Very simple thing. I'm explaining in a brief manner. Not in a what we call clear way. In a brief way. Just listen. For these 2 conductors, whenever we are applying some voltage, because of the voltage application, there is some voltage gradient developed on the surface of conductor. Else, electric field intensity. Listen to my words, please. Electric field intensity set up on the surface of the conductor. See, at what point the electric field intensity is very high. At what point the electric field intensity value was very high. In the sense, general answer what we can give is, it is on the surface of conductor only. On the surface of the conductor, the electric field intensity is very, very high. That's it. Again, on the surface of conductor, where it will be very high means, at the fine and sharp edges. At those places, we can find that the electric field intensity is very, very high. Okay. See, particularly if you think about this square shape of conductor, we are getting these fine and sharp edges as the corners of the square. So at this place, so-called fine and sharp edges, at these places, we can say electric field intensity is a large value. But on the circular conductor, you don't find any fine and sharp edges. on the circular shape. So electric field intensity remains same at all places on this conductor shape, we can assume. So we can say we have a uniform electric field distribution on the circular conductor, but we have a non-uniform distribution of field on the square conductor. So I can call here uniform electric field distribution. Here we have non-uniform electric field distribution. See, because of this high electric field intensity at the fine and sharp edges. We can say possibility of getting corona will be more on the square conductor compared to circular. Okay, so corona will be more on this. But whereas on the circular shape, corona will be less. You can say corona will be less. Could you please tell me now, in the view of corona, which conductor is suggestible? Which conductor is suggestible in the view of corona? Obviously, we should move with the circular shape of conductor rather than the square shape of the conductor. That's why all the time we used to prefer to take the shape of the conductor as a circular shape to to minimize the electric field intensity, or you can say to minimize corona in the conductor. Okay. Now, let's move ahead. Yeah, how it is high in the edges means it's a different what story. We have some techniques like finite element method and all to find out the field intensity on the surface of the conductor. I'm giving only conclusion. I'm giving only conclusion here. Yeah, so let's move. Let's move to this place. You see solid conductor, just I will show the picture of the solid conductor to you. Just it's a circular shape conductor as we said just now. Circular shape, and this complete, it's a solid body. It's a complete conductor body only. Total, it's a conductor body. Like this you can see. Solid conductor. Whereas a hollow conductor, I will be showing the hollow conductor picture in this manner. Just observe. Okay. So like this, you can see that hollow conductor. Only you have the conductor portion here. You have the conductor portion only in this place. Inner part of the conductor will be occupied by air. Inner part of the conductor will be occupied by air. Inner part of conductor will be occupied by air. So that's the shape of the hollow conductor to be expected. One small comparison I want to make. One small comparison I want to make between these two. Between these two. Yeah, please complete it if you are writing. I'll move to next slide to take up that small comparison as I said you. See, for the same current rating, same current rating, which conductor radius looks to be large here among these two? Among these two for same current rating, which conductor radius looks to be large? Is it hollow or solid? Is it hollow or solid? Definitely hollow. Why it is so means major portion of this conductor is occupied by air. Na? Major portion of this conductor is occupied by air. So this overall radius of the hollow conductor looks to be bigger. Definitely compare it to this solid. Okay, so that's a statement what I'm going to make here. Radius of hollow conductor is to be greater compared to radius of solid conductor. Radius of solid conductor. Okay. Or same current rate. Physical radius I'm saying. Yeah, so I will try to mingle all the things together at some point now. Just listen. I'm taking up a small discussion again. Very simple discussion. Just look. So I am showing one element in the system, in the power system network. Okay, so like this we have one element. For this element, we have number of lines incoming and number of lines outgoing also. I'll show. These are some incoming lines. And we have some number of outgoing lines here. Like this, we have number of outgoing lines. Okay, this one equipment, apparatus in the system for which we have number of incoming lines tighted, connected. Number of outgoing lines are connected. What we call this equipment? Anybody? What we call this equipment? These are incoming lines and these are outgoing lines. And what we call this equipment? That is going to be called generally as a bus bar. This is going to be called as bus bar. That equipment is going to be called as bus bar, or that apparatus is going to be called as bus bar. Okay, so I am asking one very simple question to you. Simple question. In which part of our system network? This bus bar is a major equipment? In which part of our system network this bus bar is a major equipment? Tell me please, which part of power system network this bus bar is a major equipment? So it's in the grid actually. It's in the grid, not in T&D. It's in the grid. What's the definition of grid actually? What is the definition of grid? It's the interconnection of number of systems together. Interconnection of number of systems together. Who is going to give that interconnection? Obviously, bus bar. So bus bar is a major equipment in grid, we can say. Okay. So I'm writing now bus bar. It's a major apparatus in the grid. Major apparatus in the grid. See, at remaining other places also we will use a bus bar. Maybe in substation we will use a bus bar. Okay. In the generating station we will use a bus bar. At some other place also we will use a bus bar. But the bus bar what we are using in the grid is the major equipment, because the definition of the grid itself is that one. Okay. Now listen here. Listen. I'm going to tell one very simple discussion here. Just look at this one. For example, listen to this. For example, if the bus bar conductor you assume, it's a bus bar conductor and it's a very smooth one. For example, if it's a power conductor is this, and this is a bus bar conductor. See, we have to connect this power conductor to bus bar. We have to connect the power conductor to bus bar. Means how will you connect that? We have to twist. We have to twist the power conductor onto the bus bar like this. We have to twist the power conductor onto the bus bar like this. See, earlier you observe that we have a smooth surface of bus bar, but because of this connection, what you have made, the surface is becoming uneven. Following all of you. So because of that uneven surface, electric field intensity will be definitely high. So not only one, we have number of joints like that. We have number of joints in that manner. Because of those joints, it is expected that electric field intensity on the bus bar conductor is very, very large. Very, very large. Right? So let me write it. So number of interconnections are there. Surface is uneven. So corona will be more. This is one point what you have to remember. Corona will be more. Yeah. Tell me, in the view of corona, which conductor we have to select for the bus bar? That's the question. Actually, this is a way how you have to understand. Because of number of interconnections, corona is more on the bus bar. So how we have to select the conductor means that conductor selection is done in such a way that conductor should have less corona. Conductor should offer less corona. In such a way, if you select, then definitely we can expect that the corona will be less in the bus bar, even though we have the interconnections, or even though we have a surface of uneven in nature. Yeah. I don't know whether you have understood this point or not. Have you understood this? Yeah. Now tell me, among these two conductors, which is suggestible? Is it solid or hollow? Hollow conductor will be suggestible. Why it is so means that is having more radius in the sense electric field intensity on the hollow conductor surface will be less compared to electric field intensity on the solid conductor. That's why most of the times for the bus bar, hollow conductor will be suggestible in order to reduce the current loss in it. Okay? Yeah. So I can say, therefore, for bus bar, hollow conductor is suggestible. Hollow conductor is used to reduce corona. Okay. Can we say electric field intensity is non-uniform at the bus bars? Yes, definitely. Yeah. So I'm repeating now. Very simple thing. Sanchit Tiwari and Aishwarya, just listen. Very simple. We have a bus bar conductor. assume irrespective of hollow, solid or anything, just we have a bus bar conductor. We have to connect the power conductor to the bus bar. We have to connect the power conductor to the bus bar. Whenever we are connecting the power conductor to the bus bar, it is creating one uneven surface. Some joint is there, na? Mechanical joint. Fine and sharp edge was formed. Because of that, corona will be more. Not only one joint, we have many joints on the bus bar. We have many joints on the bus bar, so that the bus bar will experience very high electric field intensity. So corona will be very, very high on the bus bar. That's one carbon. So because of joints, because of fine and sharp edges, corona is more in the bus bar. So we have to select the conductor in such a way that conductor should experience less corona. We have to select the conductor in such a way that conductor should experience less corona. In that view, I am selecting the hollow conductor rather than the solid conductor, because the hollow conductor is having less field intensity compared to solid. So I think you are clear now. Is it okay? Yeah. So now, so I will be moving with the solid conductor first. I don't discuss about hollow conductor further. I will be discussing about solid homogeneous composite stranded in this chapter. Okay. While we move into the next chapter, I will be introducing the bundle conductors too. Okay. First one, let me take up solid conductor quickly. First type of conductor is solid. Very simple one. Solid conductor. Yeah. Okay. So I'm showing. Solid conductor as a big picture. First, it's a single solid body. Let me assume this is a cross section of conductor for time. Okay. See, what we are going to discuss mainly in this one is current distribution, particularly AC current distribution in this particular conductor we are going to discuss. Okay, listen kindly. First of all, you assume some direction of current flow initially. In this particular conductor, you assume some direction of the current flow. I think already, listen, stop writing, just listen. Already you might be knowing about symbols of cross and dot. Okay, for example, if you take cross like this, cross. What's the meaning of cross? Current going in, Dot means current coming out. Okay, see, this is the current direction in the conductor initially. AC current flow direction in the conductor initially. Okay, so it's a AC current direction. AC current direction in the conductor. Next point. Simple. See, as and when current is flowing into, definitely some magnetic flux is going to be created. Inside the conductor I'm talking. Magnetic flux is getting created. So that magnetic flux direction we have to find by using right hand thumb rule. Let me show that. So it's the center of conductor. So as and when we have a current of this crossing nature, according to right hand thumb rule, we get the flux inside the conductor something like this. Okay, so this is the direction of the alternating flux created. All of you understood this? Please tell me till this point. Very simple thing. I need your response. Kindly, have you understood this? Nothing we have discussed. We have taken some direction of current. According to that current, we have taken up the direction of the flux created inside the conductor. That's it. What is the nature of this flux? Is it constant or alternating? Is it alternating flux or constant flux? Definitely alternating. See, whenever we have that alternating flux creation inside a conductor, definitely it will lead to some EMF induction. Okay. That EMF in turn will create some current. That current direction we have to identify now. That current direction we have to identify. Again, that current direction we have to identify by using right hand thumb rule. Right hand thumb rule. Yeah, listen please, listen please. So I am showing two circles here to identify the direction of current. Don't confuse, don't confuse. I am saying you, flux is flowing in this direction. Thumb is flux now. Thumb is flux. Flux is flowing in this direction. Current will be fingers. Current is coming in this direction. So according to that right hand thumb rule for the second time application, so as a flux is flowing like this, you can have here dot and here you can get cross. Have you understood this? Tell me, have you understood this? Yeah. Very simple, very simple, simple. Just try to understand. Already we have given the flux direction. Flux direction. Now we are applying again right hand thumb rule. But now flux is thumb. Flux is thumb. Fingers will be current induced. Now I have given the current direction inside the conductor. What it was induced now. Current direction we have given inside the conductor what it was induced. But now we are forgetting one thing, that Lenz law. Lenz law we have to apply. So by the application of Lenz law, what will happen is this induced current what you are saying now, it will be simply reversed. Induced current direction will be reversed. So like that we have to reverse the current direction. Yeah, next thing. Same. Step number one. Actual AC current direction or AC current direction initially. AC current direction. We have to assume something. Step number two. Right hand thumb rule to find out the flux direction by right hand thumb rule. Right hand thumb rule. Okay. Third one. Because of this flux, there is a current induced. That induced current direction again by using right hand thumb rule. Induced current direction by right hand thumb rule. It's for second time we are applying. And next, reverse the current by Lenz law application. Fine. Lenz law application. Okay, so let me repeat these steps again and again on this quickly. Make it clear. So first AC current direction we have taken, flux direction I have found. Now I keep two circles here. Now I am applying right hand thumb rule. According to right hand thumb rule, flux is down. So this will come to be cross and this will come to be dot. But after applying Lenz law, it will be reversed. So it will come to be cross and this will be dot. Okay, next. Again, I will take one more portion. Maybe here. I'll take one more portion here. So AC current direction, flux direction. Now I am going to take induced current. Flux is upward. So inner circle cross, outer circle dot. Inner circle is cross, outer circle is dot. But now I have to apply Lenz law. After applying Lenz law, this will become cross and this will become dot. Like this we can see whatever the blue color current I have given here, blue color current, that is a induced current inside the conductor extra. See, already existing current is there. This AC current what I have shown, this is there. Along with that, listen. Along with that, there is some extra current induced inside the conductor. There is an extra current induced inside the conductor. So it is a induced current inside the conductor. Induced current inside the conductor. Okay. What we name that current? Anybody? Anybody tell me what we name that current? What we name that current? That is going to be called as eddy current. That's going to be called as eddy current. It's a eddy current induced. Eddy current induced. You can call it as IE. Shortly, you can call it as I. Okay, very simple thing. Very simple thing now. Just observe. Just observe what I am saying. What is the resultant current in the conductor? What is the resultant current in the conductor means whatever the AC current you considered here, whatever the AC current you have considered here, that in addition to AD current, sum of these two is a resultant current flowing in the conductor by means of superposition principle. Is it clear? Now tell me, nearby the surface of conductor, what is the eddy current direction? Cross. Eddy current direction is cross. AC current, cross. Both are aiding together. So the resultant current nearby the surface will increase. Resultant current nearby the surface will increase. Okay. And how is a eddy current inside the conductor? Dot. Eddy current inside the conductor is dot. AC current, cross. So this dot current what we have now, it will be opposing the cross current. So the net current is cross only. Net current will be cross only, but that value will be less compared to surface. That value will be less compared to surface. So the conclusion what we have to make here is the current concentration is very high nearby the surface of conductor and current concentration is very less inside the conductor. This is going to be called generally skin effect. This is going to be called as skin effect in the conductor. So have you understood this? Are you clear? Yeah. Yes. So who is a cause for skin effect? Who is a cause for skin effect in the conductor? Eddy currents. Eddy currents creation. Eddy currents creation is a cause for the skin effect. Okay. So I'm writing the things. Kindly go through. I'm writing the things. Kindly go through. First point I'm writing. I.e. eddy current induced nearby surface of conductor is in the same direction of AC current flow, in the same direction of AC current flow, therefore net current concentration is very high nearby the surface. Okay, next thing. Same thing I will copy. IE induced inside the conductor. Inside the conductor is in the opposite direction. Of AC current flow. So net current concentration is very low. Inside the conductor. Very low inside. So this we are going to name as skin effect. Okay. So this is called as skin effect. So it's better to answer the skin effect in this manner. It's better to answer the skin effect in this manner. It's a tendency of alternating current. Tendency of alternating current to be concentrated highly nearby the surface of the conductor. Okay. So it is a tendency of AC current to be concentrated nearby surface or skin of the conductor. Surface or skin of conductor. Nearby the surface or skin of the conductor. Yeah, please complete it quickly. On the outer surface, how it is aiding, both are in the same direction, right? Akash. Both are in the same direction. Eddy current cross, AC current cross. Both are aiding together. Both are in the same direction. That's the meaning. Yeah, I will show previous play. I will show previous page. Sir, why we apply Lenz law? Effect opposes the cause. Vamshi, to show that the effect is opposing the cause, we have to apply Lenz law, right? I've shown the previous page. Kindly come. Yeah, so let's move to the resultant current flow in the conductor. Yeah, so I'll show almost the same conductor here. This one. Listen. What is the net current direction? Tell me all of you. What's the net current direction nearby surface or inside the conductor? Net current direction. That's what Shiva I am saying you. Lenz law in the sense effect is opposing the cause. In the sense we have to reverse the direction of current in order to oppose the cause. Net current will be cross only always. Inside or outside nearby surface, whatever it is, it will be cross direction. Cross direction, but the cross is of high magnitude nearby surface, but of less magnitude inside the conductor. Okay? Yeah. So I'll say here. So the net current is highly concentrated nearby surface. It will be of the symbol cross. Okay. And inside the conductor cross, but that's of less magnitude. It's of less magnitude. So I'll show something like this. Yeah. So like this. Next thing. So I'm taking up one term here, that is skin depth. Skin depth. So I don't write definition. Equation is our concentration. Okay, kindly observe. Skin depth means it's a depth of the conductor from surface. Depth of the conductor from surface up to which current concentration is very, very high. Observe my words, please. Current concentration is very, very high. Not non-zero. Up to the portion where the current concentration is very, very high, that we are going to name it as skin depth. So I'll show this, maybe this portion. Highly concentrated portion, we are going to name as skin depth delta. not the complete non-zero current portion. Only this portion where we have a high concentration that we are going to call as skin depth delta. So I'm giving formula for this one. It's one of very important formula, delta skin depth square root of 2 by omega mu sigma. It is a formula for the skin depth. Delta is equals to square root of 2 by omega mu sigma. Omega mu sigma. Okay, so that omega it's a 2 pi into frequency. Omega it's 2 pi into frequency. Okay, and this mu is mu naught into mu r. Mu is like mu naught into mu r. Sigma is a conductivity. Sigma it's a conductivity of the conductor. Electrical conductivity of the conductor. Okay, next thing. Kindly observe what I am saying to you. I am asking one very simple question. If that skin depth is more, listen to my words, please. Skin depth is more. How is the skin effect? Depth is more. How is the skin effect? Less, obviously. Okay, yeah. So if the depth is very less, depth is very less, current is very close to surface, then obviously I'll say skin effect is more. Tendency of concentration is more nearby the surface. Okay, that's the relation between delta and the skin effect. So I'll say as delta is decreasing, skin effect, I'll say it's more. Skin effect is more. And as delta is increasing, I can say skin effect is decreasing or less. Skin effect is less. That's the relation. Okay. Next thing. Listen to this. For example, I'll ask one very simple question to you. Ideal conductors. Ideal conductors. Does it have skin effect or not? Ideal conductors. Does it have skin effect or not? Tell me, please. For ideal conductors, do we have skin effect or not? Okay. What do you mean by skin effect, sir? What do you mean by ideal conductor here? All of you listen. What do you mean by ideal conductor? Zero resistivity or infinite conductivity. Yes or no? Sigma is equals to infinite, you can say. For ideal conductors, we know sigma is equals to infinite. Okay. See, sigma is equals to infinite means what is delta value? If sigma is infinite, what's the delta value? 0. Then delta is equals to 0. So there is no depth at all. There is no depth of current. So where the current will be now? If delta equals 0, current is concentrated only on surface of conductor. Then how is the skin effect here? How is the skin effect in the ideal conductor? Maximum. Skin effect will be maximum, but resistance is equals to 0. Skin effect is maximum, but resistance is equals to 0. That's the thing you have to identify now. Okay, so I can say maximum skin effect will be experienced by the ideal conductors. Maximum skin effect will be experienced by the ideal conductors, but resistance value is equals to 0. But resistance value is equal to 0. Okay, but resistance value will be equals to 0. That's the thing. Next thing. Listen, please. Listen. See, if the operating frequency was increased, what will happen to skin depth? Decreases. If frequency is increasing, means omega is increasing, delta is decreasing. If delta is decreasing, skin effect is going to increase. Means I can say skin effect will be directly proportional to frequency of operation. So with respect to frequency, skin effect also going to be increased because skin depth is decreasing. Okay, so I'll say skin effect directly proportional to frequency. Skin effect is directly proportional to frequency. All of you following this conclusion, what I am saying you, skin effect is directly proportional to frequency. Yeah, next thing. With respect to relative permeability, if relative permeability is more, depth is less, skin effect is more. So skin effect proportional to mu r. Next, of course, it depends upon the sigma value also. You can write sigma here. So F into mu r into sigma. These are the three factors which is deciding the skin effect. Okay, next, I want to compare resistance of the conductor from DC supply to AC supply. First, you tell me, for DC, do you have any skin effect for DC? For DC, you tell me please. Do you have any skin effect? Yes or no? No. What's the reason? Very simple reason I want. Frequency is 0, na? So if the frequency value was 0, frequency is 0 in the sense delta will be infinite. Infinite depth in the sense, obviously I will be assuming that the current distribution is uniform throughout the cross section of conductor. So we don't have any skin effect for the DC supply. But for AC supply, we have a skin effect. So by that way, current flowing area, look my words please. Current flowing area through which current is passing is different in AC and DC. Yes or no? Because of that area variation, net cross-section area variation, definitely there is a change in the resistance value in the AC supply as compared to DC. That comparison we are going to study briefly. Okay, so I'll say first here, for example, case 1, you take DC operation. It's a conductor. He is excited with a DC supply like this. And it's a current of IDC. Okay, simple. Frequency is 0, as we said just now. Delta is equals to infinite depth. So you write no skin effect here. No skin effect. So as you don't have any skin effect, the current is getting concentrated throughout the cross section and it is uniform. Even as compared to current, the better word to be used is current density, J. J is uniform, right? J is uniform. Current density is uniform. Now, in the whole area, the current is passing. The whole cross-section area, the current is passing. And how much area that current is passing means simply pi r square. Now, resistance of this conductor for DC supply is equal to rho L by total cross-section area of the conductor. Resistance of this conductor for DC supply will be rho L by total cross-section area of the conductor. Okay, so total cross-section area of the conductor. Now let me take case 2 for AC. I'm taking case 2 here for AC. Case 2. Yeah, same conductor we have taken like this. But here we have AC supply, AC voltage. Okay, and this conductor is carrying some AC current. But the frequency is non-zero. So delta will not be equals to infinite. Skin effect exists in the system. So because of the skin effect, you know, current concentration is very high nearby surface and it's very low inside. Current density is non-uniform, right? J is non-uniform. J is non-uniform. Okay. Now, in how much area that current is passing? Definitely less than A. Definitely less than A. So I can say A dash here, A dash. It's a AC current flow area. AC current flow area, which is definitely low compared to total cross-section area of the conductor. Definitely less compared to total cross-section area of the conductor. Now you can write the conductor resistance for the AC supply. Conductor resistance for the AC supply. Rho L by A dash. Conductor resistance for AC supply is rho L by A dash. Okay. Yeah, please complete it quickly. In the next slide, I will be taking up the ratio between these two resistances and we'll make some comment. Yeah. So now if you take up that ratio, AC resistance of the conductor to DC resistance of the conductor, what you'll get from this? Rho L by A dash in the numerator, rho L by A in the denominator, it will turn to be A by A dash. A by A dash. Okay, next. Who is saying this difference between AC and DC resistances here? Who is saying that the AC resistance is different from DC resistance? Skin effect. So this ratio what we have now, that ratio what we have now, that I am going to name, as factor of skin effect, K. It's going to be called as factor of skin effect. Factor of skin effect. So conductor resistance for AC supply will be equals to K into conductor resistance for DC supply. Conductor resistance for AC supply will be equals to K into conductor resistance for DC supply. Okay, how is the value of K to be expected? Definitely greater than 1. Definitely greater than 1. So as that K is greater than 1, definitely conductor is going to offer more resistance for AC supply compared to the DC supply. Conductor will offer more resistance for AC supply compared to DC. Okay. So what's the problem of having more resistance for the conductor? Definitely power loss is more, voltage drop is also more. So those are definitely disadvantages of having higher resistance for the conductor. So you can write now, because of this, voltage drop will increase as well as power loss also increases. Power loss also increases. These are the disadvantages. So actually in the starting class yesterday, we said that the desirable characteristics of the line is maintaining low voltage drop as well as low power loss. Yes or no? But if you are using solid conductor, both values, power loss is more, voltage drop is also more. So we can't use a solid conductor now. Not only that, we should make an attempt to reduce the skin effect. Not only avoiding the solid conductor usage, you have to attempt to reduce the skin effect in the conductor. So to know how to reduce the skin effect, first we should know on what factors the skin effect will be depending. Already we said some factors now. What are the factors here? Frequency, mu r, sigma. We will search for some other factors and we will make the conclusion and we will tell how to reduce the skin effect in the conductor further. Okay, so our next heading will be factors on which the skin effect will be depending. Skin effect depends. Factors on which the skin effect will be depending. Okay, so already we said 3, frequency, mu or sigma. Now we are searching for some other factor. Kindly observe my words. Kindly observe here. Very simple thing. Don't confuse. Very simple thing. Just observe. I have one solid conductor, something like this. This one solid conductor I have. It's having some area of cross section A. Listen, please. Don't write. Just listen to me. Area of cross section A. We are sending some AC current. In that, and that AC current is getting concentrated up to a depth of delta, you assume. Getting concentrated up to a depth of delta, something like this. So we have the current flowing area as A dash. Current flowing area as A dash. Now we have the K, which is A by A dash. That's it. K value something like A by A dash. All of you understood till this point? Very simple. Nobody is responding. Is it clear? Okay, done. Next, listen now. Same conductor, look, same material, same frequency of operation. Size of the conductor was increased. Size of the conductor was increased, means area. Area of cross section I have increased. Something like this. Okay, now area of cross section value was increased. If you check for the current concentration, current is concentrated nearby the skin, something like this. My question is, do we have any change in the delta skin depth? Is there any change in the skin depth value? Anybody? Anybody please tell me, do we have any change in the skin depth value? No. Because skin depth depends upon what? Frequency, mu r, sigma. Those values are remain same, right? Skin depth is not going to be changed at all. Skin depth is not going to be changed at all. Skin depth remains same. But what will happen to A dash value? Current flowing area, what will happen? It will increase because surface area was increased, right? Because of increment in the surface area, A dash value is going to be increased. Right? Area of cross section increasing. Current flowing area also going to be increased. What will happen to K number? A by A dash. What will happen to K number? That's the question on which we have to talk. A by A dash, K value, what will happen? That will decide whether the skin effect is getting increased or remains same with respect to increment in the size of the conductor. Okay, let me take up a small discussion again. This K value we are talking now. K in this case, K. See, total radius is smaller. Just look once. Total radius is smaller. So overall cross section is pi r square. Pi r square is a total cross section of the conductor. By A dash. A dash means only this red color area. A dash means we have to consider only red color area. Okay. So this depth is delta. Depth is delta. Now, up to this point, the radius is r minus delta. Are you clear? This point, are you clear? Tell me please. Depth is delta. White color area, current, no current flow area. No current flow area, radius is r minus delta. No current flowing area, radius is r minus delta. Now tell me, what is the area of current flow? What is the area of current flow means? From the total area pi r square, we should remove this white color area. What is that white color area? Pi r minus delta square. Okay, it's an approximation. It's not exact one. It's approximately, not exact, approximate. So let me continue with this approximation a little bit further. Okay, approximately. Pi r square numerator, denominator, pi r square minus, you expand it and you write it finally, what you get here is 2 pi r delta minus pi delta square. Like this you will get. Just check it. Check it once. Are you getting it? Okay, now radius of conductor was increased, na? So numerator was increased. Radius of conductor was increased. Denominator also increased. But which increment is more? Which increment is more? Is it numerator or denominator? In the numerator, we have a squared increment. Numerator, we have a squared increment. Denominator, we have only r increment. So numerator increment is dominating the denominator increment. So the value of K definitely increases. Value of K definitely increases. So in the similar way, in this previous diagram, area of cross section of conductor is increasing. Current flowing area is also increasing, but that ratio what we have now, that is going to be definitely increased. Definitely increased. So in a bigger size of conductor, the skin effect will be definitely more compared to smaller size of the conductor. Okay, so skin effect will be more in this one. More skin effect. So the conclusion what we can make from this complete analysis is skin effect will be proportional to physical cross-section area of the conductor. Physical cross-section area of the conductor. Skin effect will be proportional to physical cross-section area of the conductor. A dash is the depth area. Yes, correct. A dash is a depth area. Red color area. Now finally, what we conclude here is skin effect depends upon three factors according to our discussion. Skin effect is proportional to frequency, mu r, sigma, area of cross section. These are the factors on which the skin effect will be. Okay. Now, in order to reduce the skin effect, that's what our aim, of course, what we have started. We have to reduce the skin effect. To reduce the skin effect, we have to control these factors. Already frequency is a fixed number. We can't change it. Frequency, it's a fixed number. We can't change it. We can't reduce it to reduce the skin effect. No choice from frequency. Mu r, already material you have selected. What material? Aluminium. For that aluminium, mu r is equals to 1. Both for aluminium and copper. Aluminium and copper. Of course, it's the lowest number for any material. So mu r value we can't decrease. Mu r value we can't decrease. Kindly understand? Kindly understand quickly what I'm saying. Mu r value we can't decrease. Sigma, by reducing sigma, skin effect will decrease. By reducing sigma, skin effect will decrease. But by reducing sigma, overall resistance of conductor will increase. Na? DC. DC resistance of conductor will increase. So reducing sigma is not at all suggestible to reduce a skin effect. In order to reduce the resistance, in fact. Okay. What's the other option? Reducing the area. So reducing area means what? Reducing area. If you are reducing area, skin effect will decrease. That's okay. But current rating of conductor is going to be reduced. So reducing area is also not suggestible. So getting my point? I said 4 options here, but 4 options are having their own disadvantages. We can't use these 4 options at all. Then you please tell me who is a cause for skin effect? Basic reason. Basic reason. Who is a cause for skin effect? Basic reason. Eddy currents. Eddy currents is a reason to get the skin effect. How to reduce the eddy currents? How to reduce the eddy currents? We have to do lamination. To reduce the eddy currents, we have to do the lamination. Lamination means here what I do is, rather than using a big solid conductor, I will cut that conductor into number of small solid conductors. I'll cut those big conductor into number of small solid conductors. And then we bundle them, or we combine them, or we compress them, and we will twist to make a resultant conductor. In that, the skin effect will be definitely less. That conductor we are going to name as stranded conductor. Stranded conductor. By using stranded conductor, we are capable to reduce the skin effect by reducing the circulation of the eddy currents. So, all of you getting this point? And I will write that point here. By this means to make up that conductor at the same place, because we have number of wires, right? Number of wires. By twisting only, you can keep all the wires mechanically tightened. Okay. So to reduce a skin effect, the option what we are suggesting is skin effect. Stranded conductors has to be used. Stranded conductors will be used. Conductors will be used. Okay. stranded conductors will be used, in which eddy currents will be less. Eddy currents will be less. Okay. Eddy currents will be less. Yeah. So we stop class at this point. If you have any doubt, you can ask me. The class is over. Class is completed. If you don't have a doubt, you can. Ramesh.
Yes, sir. Good morning, sir.
Ramesh.
Sir, second problem, I2 is equal to 1 by n I1.
Hello.
Sir, in second problem, you take I2 is equal to 1 by n I1.
Okay.
How is it take, sir?
From first problem.
First problem, we get I2 is IT is equal to N1 into I1, sir.
1 by n into I1. Cross check once.
Okay, sir. Clear, sir. Thanks.
Yeah. Fine. Yugashri.
Sir,
Tell me.
sir, if the area is increase or decrease, K is same, sir?
A dash will change, right?
Yes, sir, but you told that if the size is increase, area of the cross section is increase, K is equals to A by A dash, you told, sir.
Okay.
And if the small cross section area is a small, K equal to also A by A dash.
Yeah, correct.
That's why I'm asking.
That ratio will come very close to 1.
That's why I'm asking K is same for small.
K is not same for all. The A increment is dominating the A dash increment, right?
Yes, sir.
So obviously numerator increment is more compared to denominator. That's what I have proved here. Numerator is a R square increment. Denominator is only R increment. Numerator increment is dominating the denominator increment, so K value will increase. Getting?
Okay, sir. Okay, sir.
That's it, Yogeshri?
I'm asking that only, sir. Is the same or not? I'm asking. The increase now,
K
sir.
value,
A dash
will be,
is
different. K value
A
will be different for each and every conductor.
Yes,
Each
sir.
and every size of conductor.
Okay.
That depends upon size of the conductor. Okay?
Okay, sir. Okay. Hello.
Vikrant. Vikrant?
Hello.
Vikrant, do you have any doubt? Okay. Manjunath.
Good morning, sir.
Tell me, Vikrant.
Hello.
Tell me, please.
Sir, am I audible?
Yeah.
Sir, actually నా డౌట్ వచ్చేసి నిన్నటి క్లాస్ లో సార్ నాకు నిన్న ఛాన్స్ రాలేదు.
Okay. Tell me.
నిన్న అది మనకి ట్రాన్స్మిషన్స్ లైన్ లో లైట్నింగ్ వచ్చినప్పుడు అందులో కరెంట్ ఇండ్యూస్ అవుతుంది, దాని ద్వారా ఎంఎంఎఫ్ ప్రొడ్యూస్ అది కండక్టర్స్ తో లింక్ అయ్యి ఈఎంఎఫ్ ఇండ్యూస్ అవుతుంది అన్నారు కదా సార్. ట్రాన్స్ఫార్మర్స్ మీద టవర్స్ మీద గ్రౌండెడ్ లైన్స్ హైట్ ఉంటాయి కదా సార్, అంటే టాప్ లో ఉంటాయి కదా, వాటికి కండక్టర్స్ కి హైట్ డిఫరెన్స్ ఉంటుంది కదా సార్, అయినా కూడా ఎంఎంఎఫ్ అనేది ఫ్లక్స్ లింకేజెస్ అవుతాయి అంటారు సార్.
ఫ్లక్స్ లింక్ ఎందుకు అవ్వదు? ఎంత డెప్త్ కైనా పోతుంది కదా ఫ్లక్స్, బట్ ఇంటెన్సిటీ ఎంత ఉంటుంది అనేది మ్యాటర్ అక్కడ.
ఇంటెన్సిటీని బట్టి ఇండక్షన్ అనేది
Yes. Induction will be decided by the distance, definitely.
Yes. Okay.
Even
అదే
though
doubt,
distance
sir.
is a good amount,
Hmm.
it may not be a distance like distance between conductor and ground, right?
Yes, sir.
It's not too high. It's not too high like number of kilometers. It will be in the order of meters only, right?
Yes.
So definitely there is an
అండ్
induced
అదే
area.
లైట్నింగ్ నుంచి వచ్చే కరెంట్ ఎక్కువ ఉండటం వల్ల ఆ డిస్టెన్స్ అనేది పెద్ద మ్యాటర్.
Obviously, no, flux magnitude will be more.
Okay.
Even though the distance is a bit more, definitely there is a possibly
Okay.
induced area.
Yes. Got it, sir.
Okay, okay.
Thank you, sir.
Sir, am I audible?
Tell me, Manjunath.
Sir, once explain why compensation is not advisable in distribution, sir.
At how many locations you keep capacitor bank?
We have to keep it in many locations.
That's why it's not economical, no? Getting what I said, Manjunath?
Yes, sir. Yes, sir.
Yeah. If the people want to keep those capacitor banks, so to install the capacitor banks only, we have to create a separate company. Yes or
Yes,
no?
sir. Yes, sir.
So that's not at all economical. Prithviraj,
Hello, sir.
tell me, Prithviraj.
Sir, 41F, sir.
Okay,
Sir, before that one 40F, sir.
okay.
Sir, here, before you said distribution levels, primary distribution level 11 kV will be 3-phase 3-wire. But when we are taking receiving and substation like 33 kV, 11 kV, when we are taking delta star ground, it will go for a 3-phase 4-wire, na, sir?
Yes, yes.
Then it should be delta by delta, na, sir?
Why delta by delta? Why can't it be delta by star?
Means we are using ground terminal also.
Already this is grounded, na? This neutral is grounded, right?
Yes, sir.
This neutral is grounded. So up to this point, ground is acting as a neutral wire.
Ground is acting as a neutral wire. Means we will run only 3-phase 3-wire with delta star configuration.
Yes. From this also you get 3 wires only.
Okay, sir. Okay, sir.
Okay. Ground is going to act as a neutral wire.
Okay, sir. Thanks.
Okay. Bhaskar,
Hello, sir.
tell me, Bhaskar.
In last slide, skin depth is the same and how the current flowing area is increasing, sir.
Surface area was increased, no, Bhaskar?
Skin depth is same, na, sir.
Skin depth is same, thickness is same, physical size is increased.
Okay.
You compare this with a hollow, you can get it.
Okay, sir. Induced current value is small or big, sir?
That depends
Eddy
upon
current.
actual current flow, strictly.
Means that only the deciding skin effect, na, sir.
That is one of the factor, but after cancellations and all, the people will say skin effect is independent on the current value.
Sir?
Skin effect will be independent on the current value because eddy current value depends upon the current, right? Again.
Yes, sir.
So because of that, the current flowing area for AC current is almost independent on the current value.
Okay.
How much it is flowing.
Sir, here one graph is said, no, sir, that cost is decreasing when the voltage is increasing.
Okay.
How it is decreasing, sir, cost?
Because conductor cost decrement may be dominating the increment in the insulation cost.
Okay.
Beyond that level, beyond certain level, insulation cost increment is dominating the conductor cost decrement.
Okay.
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 Yeah. Any other doubt you have, Bhaskar?
No, sir. No, sir.
Yeah. Avinash,
Hello, sir.
tell me, Avinash.
Sir, in the last slide, you are told about the skin effect when the area is reduced, and sir, please tell that factors once again.
See, if area is decreasing, skin effect is decreasing. Okay. But if you are reducing area, current rating will decrease, right?
Yes, sir.
So it's not suggestible.
Okay, sir. And this, sir, row, sir?
Sigma.
Sigma, sorry, sir. Sigma.
If sigma is decreasing, skin effect will decrease. Okay. But if sigma is decreasing, resistivity will increase for conductor.
Yes, sir.
If resistivity is increasing, conductor resistance itself will increase, right?
Yes, sir. Resistance will increase.
Then skin effect decrement will not give any advantage to you.
Okay, sir.
Okay. Our aim is to reduce the resistance of conductor. But we are losing our aim, right?
Yes, sir.
Yeah.
Thank you, sir.
Yeah. Swain.
Hello, good morning.
Tell me,
Sir.
Swain. Tell me. Good morning.
Sir, here you have said in the bus bar, connected hollow conductor to reduce the electric field.
Okay.
Okay, but in general, when the transmission line is there, then we have a bundle of conductor, so that how can a bundle of conductor can be merged with the bus bar with the, that hollow conductor, from where we take hollow conductors? Means to join with the bus bar or to react with the bus bar conductor.
No, what's the problem you are getting now with this?
Means how to, we have conductor with a solid conductor actually, but how from where we can take hollow conductor to wrap the bus bar conductors? You have said a example with some practical example.
No, see, wrapping the conductor over the bus bar may not be possible. Okay, so we will put a hole for the bus bar.
Okay.
And we will push the power conductor into that hole.
Yes.
By using nut and bolt, we'll fix it.
Okay.
That's the practical method.
Yes.
Twisting is not possible.
And another doubt is there in the AD in the 53 page. Here, according to Lenz law, it opposes the cause.
Yes.
Cause is the main current, that AC current we are trying to flux is produced due to that conductor, that current, that AC current, the flux is produced due to that AC current, the main AC current.
No. Who is creating eddy current?
Eddy current is creating due to flux.
So flux is a cause, eddy current is an effect.
Okay.
Effect should oppose a cause.
Then
you take the direction of current from this eddy current, direction of flux from eddy current.
Then
is it opposing phi or supporting phi? That you check. For example, cross you have going in. So that flux, whatever you say now, that will oppose a phi, right?
Yes.
Dot, that will also oppose a phi.
But here, according to Lenz, both is satisfying. One direction current is opposing the flux, another is supporting. Means current
both are opposing only. Check once.
Opposing only the flux.
Both are opposing the phi. Both directions of eddy current flux is opposing phi.
Okay, but not the current is the cause. Actually, the main current.
No.
Not okay.
Okay.
Okay. Thank you, sir.
Yeah. Vishwanath?
Hello, sir. Am I audible, sir?
Tell me, Vishwanath.
Sir, actually, can you please say me about the relationship between the skin depth and skin effect once again?
Inversely proportional.
Uh,
If depth is increasing, what will happen to skin effect?
Sir, if the depth is increasing means the
Current concentration is towards the center.
sir, if the skin, sir, can you please say the definition about skin depth?
Skin
Once
depth
again.
is a
Yeah.
depth of current flow up to which it is concentrated,
Okay, sir.
measured from surface.
If the depth is increasing means the
Current is going towards the center, right?
Yeah, sir.
Current concentration is more high towards the center.
Yeah, sir. That means the skin effect is zero.
Zero
negligible.
means decreasing, you say.
Yeah, okay, sir.
Decreasing.
And from the previous class, sir, sir, how is the voltage drop occurs in the transmission line, sir?
Simply, if current flow is there, I into Z is a voltage drop, right?
Yeah, sir.
That's it.
Okay. That's it, sir.
Okay. Sarath,
Good morning, sir.
tell me, sir.
Sir, small doubt, sir. In distribution side, how the voltage are means why the 11 kV, 33 kV, 66 kV, sir?
No, that is coming from standardization only. There is no specific reason why these are multiple of 11. Sarath,
Yes, sir.
so your doubt is why the voltages are multiple of 11.
Yes, sir.
400 kV is not a multiple of 11, right?
Yes, sir.
765 kV is not a multiple of 11.
Yes, sir.
So there is no specific reason or exact reason why these are multiple of 11. So we are standardizing the voltage levels in that way for a flexible operation.
Okay, sir.
Okay.
Okay, sir.
For example, can't we have 300 kV line?
Yes.
Are you understanding me what I am saying?
Yes, sir. Yes.
And we have 300 kV line. Can't we have 350 kV line? Can't we have a line of 200 kV? Can't we have a line of 150 kV? Yes, you can build up the line and you can connect it. But if you are changing your level of line for each and every time, number of transformers, how many you have to use to interconnect with the already existing system?
Yes, sir.
For example, 150 kV line, you want to interconnect with a 220 kV bus bar. You have to use a 150 by 220 kV transformer, right?
Yes, sir.
Again, for the same bus bar, if you want to connect a 300 kV line, you have to use a transformer of 300 kV by 220 kV again.
Yes, sir.
So number of transformers required will be very large, and as well as complexity of the system will be very high. That's why the people have standardized some voltages. So if you want to build up any new line, try to take up a voltage which is close to this only.
Okay, sir.
Okay, rather than 33 kV, can I go for 27 kV? Yes, you can go, but you have to build up a new transformer, right?
Yes, sir.
So that's a problem. That's a complexity in the interconnection. What we get if you are going for large number of voltages.
Yes, sir.
That's why we standardize the voltages and we are following only those voltages according to the requirement.
Okay, sir. Sir, another doubt. Here you said, no, sir, 3-phase 4-wire system.
Yes.
From that only we take the single phase, sir.
Yeah, correct. One phase, one neutral.
Okay, sir. So from that we get 240 volts.
230, 240, sometimes 250 also will get.
Okay, sir.
Okay.
Thank you, sir.
Yeah. Meghna.
Good morning, sir.
Good morning. Tell me, Meghna.
Sir, from yesterday's class, sir. Sir, నిన్న మీరు స్విచ్చింగ్ ఓవర్ వోల్టేజ్ ఇస్ గ్రేటర్ దెన్ లైటనింగ్ ఓవర్ వోల్టేజ్ అన్నారు కదా సార్. సో లైటనింగ్ ఓవర్ వోల్టేజ్ అనేది ఎక్స్టర్నల్ గా వస్తుంది కాబట్టి ఆ వోల్టేజ్ అనేది ఎక్కువ ఉంటుంది కదా సార్.
నార్మల్ తక్కువ ఉంటుంది చెప్పలేము. అంటే
అది ఎక్స్టర్నల్ ఫ్యాక్టర్ కదా సార్.
Okay, external means is it high? We can't say, na.
Yes, sir. అంటే మనం లో ఉంటుందని కూడా చెప్పలేం కదా సార్.
Yes, we can't say. That also we can't say.
సో
That depends upon level of surge.
అంటే మీరు ఇచ్చిన స్టేట్మెంట్ లో స్విచ్చింగ్ ఓవర్ వోల్టేజ్ ఇస్
That's the
డామినేట్.
observation. That's the observation. What we are saying is above certain voltage levels. See, one thing, Meghna, as and when we are rising the operating voltage level, switching over voltage will increase or decrease or remain same.
ఇంక్రీజెస్ సార్.
Increases. Lightning over voltage, as you said, it is external. It may be more or less same, na.
Yes, sir.
Lightning attacked on a 220 kV line. Lightning attacked on a 400 kV line may create same value of surge voltage.
No, sir.
Because external injection is same, right, in both lines.
Yes, sir.
Then surge voltage will be remain same, na, lightning surge voltage.
Okay, sir.
But switching surge voltage will be different for 400 kV. It's high. But for 220 kV line, switching surge voltage will be less.
Okay, sir.
You assume that switching surge is 2.5 times of rated voltage.
Okay, sir.
So for 220 kV line, switching surge is 2.5 into 220 kV.
Okay, sir.
Whereas for 400 kV line, it's 2.5 into 400 kV.
Okay, sir.
But lightning over voltage might be same in both cases. Because it's created by external source. It's independent on the operating voltage. It's independent on the rated voltage.
Okay, sir.
I think you are not clear.
Sir, can you explain it once again, sir?
For example, if it's a 220 kV line, it's a 400 kV line. You assume that we have a attack of lightning created a surge voltage of 700 kV. Okay? Lightning surge, 700 kV. For example, same lightning was attacked on this. How much is the lightning surge voltage experienced by this one?
Same, sir. 700.
700 kV. Now tell me, switching surge how much? 2.5 times 220 you assume. How much is switching here? 2.5 into 400. Understanding, Meghna?
Yes, sir.
You assume that switching surge is 2.5 times of rated value.
Yes, sir. It's 550.
Then there is a difference in the switching surge voltage, but lightning surge voltage is more or less same.
More, sir.
More or less same, I am saying. Lightning will be more or less same here in both cases. But switching surge voltages are different, right?
Yes, sir.
Then what's your doubt now? Tell me.
No, sir. It's clarified. Thank you, sir.
Clear. Okay, fine. Salman Khan.
Hello, sir. Good morning.
Tell me, Salman Khan.
So in practical distribution system on 40F, sir. Here, sir, I understand that for the getting the single phase supply, we used to delta star transformer to get a single phase supply. Okay, sir. But before the feeder, why use delta star transformer? Because we are getting only the line voltage, sir.
Yeah.
That I'm not getting.
No, this is delta star. Are you clear?
Yeah, this is I'm clear.
You are not clear about this delta star.
Yeah. What is the reason? Because we are taking only line voltage, sir. Means neutral is not used.
So that is for flexible flow of the zero sequence currents.
Okay.
Have you attended F&S?
Yeah, I attended. Sir.
Okay.
Okay, sir. And another doubt, sir.
Listen.
Okay.
This is a delta star ground, your substation transformer. Okay.
Okay, sir.
This is your delta star ground distribution transformer.
Okay, sir.
Yeah. So it is some source supply. Now we say you have a fault on this feeder some place.
Okay.
Do you have any circulation of zero sequence current?
In this case.
In this case, do you have any please make your voice loud.
Maybe not, sir, because there is star grounded, sir.
Please make your voice loud.
I'm audible, sir.
Little less.
Now, sir. Am I audible now, sir?
Yeah, okay. Tell me. After having a fault at this place, do you have any circulation of zero sequence current path or no?
I think no, sir, because
Why?
neutral is grounded there. At the
Zero sequence current path is there, na?
The path is there, right?
You have a delta star ground transformer. There is a closed path for zero sequence currents.
Right.
Okay, so LG current will flow. Line to ground fault current will flow.
Right.
Right. So, for example, you take a fault at this place.
Okay.
Then it's circulating in this way.
Right.
It won't go into this line, right?
Correct.
So it will circulate in this transformer. Now, what do you want to tell me? For example, you take this one delta delta.
Okay.
Then if you take a LG fault here,
Right.
is there any zero sequence current closed path?
No.
No. Then arcing grounds will occur. Possibility is there.
Right. Arcing ground possibility.
Okay, and you may ask me, sir, why can't you keep both star ground, star ground?
Yes, sir. That's also a possibility.
Okay. And in this case, there is a closed path. But who knows, in the upper side of this transformer, there may be open.
Right. There may be delta.
There may be open. We don't know.
Right.
So we, as a sub-circuit, you should close your own path, irrespective of location of fault.
Correct.
So for that purpose, better you close this with delta and you make this one star. So definitely zero sequence current or LG fault current circulate.
Correct.
Okay.
Understood.
Yeah.
There is another doubt, sir.
Tell me.
Sir, when you use a grid, in the grid, we keep the same voltage at the grid, sir, right? And supply from the various generator generating the same voltage by using step-up transformer and all. Right,
okay.
Sir? Then how is the current flow between the same voltages, sir? Grid voltage is same and generator voltage is also same.
Who said voltage is same? Rating